66 million years ago, a single impact reshaped life on Earth forever. The Chicxulub asteroid struck with unimaginable force, ending the age of dinosaurs in moments and transforming the planet. Tonight we'll uncover the scientific story behind this world-changing event. If you enjoy the journey, please like, subscribe and share, and tell us in the comments if you could witness one moment before the impact. Which era of the dinosaurs would you choose? Thank you for watching. Now let's begin. Late in the Cretaceous period, Earth moves in its steady path around the Sun, one planet among several in a mature solar system that has long since settled from its early violence. The orbit is almost circular, close enough to keep oceans liquid and climates moderate over most of the globe, far enough that surface rocks do not glow with heat. One full journey around the Sun takes about 1 year, and season follows season with slow regularity as the planet turns on its tilted axis. From far away, Earth presents a familiar pattern of blue oceans, swirling white clouds, and irregular continents in tones of green and brown, yet the arrangement of land and sea differs from that of later ages. The great supercontinent of earlier times has broken apart, and broad plates of crust continue to shift in slow motion, millimetre by millimetre each year, carrying fragments of land across the globe. The outlines of later continents are already taking shape, although gaps of shallow ocean water still cut through them in wide seaways. To the west of a landmass that will one day be called North America, the floor of the ocean dives beneath a chain of volcanic mountains, feeding arcs of fire and uplifted ranges. In the middle of the Atlantic basin, a long ridge of rising rock pushes neighbouring plates apart, widening the young ocean through continuous eruptions on the seafloor. Across what will later be known as Eurasia, Africa and South America rifts and collision zones adjust the positions of crustal blocks in a slow-shifting mosaic. There are no giant ice sheets at the poles. Instead, land near the high latitudes is often free of permanent ice, and in some regions forests reach almost to the polar circles. Sea levels stand higher than they do in many later times because warm water expands, and because few permanent ice caps lock away the planet's supply of liquid. Broad shallow seas flood low-lying parts of continents, forming wide inland waterways where once there was dry land. One such interior sea stretches across the middle of North America from what will later be high northern latitudes towards subtropical belts, dividing the land into eastern and western masses and linking two great oceans. Along its broad margins, muddy deltas, sandy shorelines and coastal plains record the rise and fall of ancient tides and storms. The atmosphere contains more greenhouse gases than in many later ages, and the global climate is generally warm. Average temperatures sit higher, especially toward the poles, and the contrast between equator and high latitude is less extreme than it will be in colder eras. In many regions, winters are mild and summers long, encouraging lush plant growth where moisture is available. Tropical and subtropical belts lie under strong sunlight, and thick layers of warm air rise and fall above them with each day's heating and cooling. Storm tracks carry moisture inland from the oceans, delivering rain to lowlands and snow only to higher mountains. The oceans themselves cover most of the surface as they do in later times, but their character is subtly different. Warm waters extend farther toward the poles, and great gyres circle slowly within each basin, driven by winds and the rotation of the planet. Narrower seaways and broad continental shelves guide currents in routes that do not exactly match later patterns, and the positions of continents help shape where upwelling occurs and where calm, stratified waters persist. Chemical balances in the water reflect a long history of volcanism, erosion, and biological activity with abundant dissolved minerals and a rich mix of elements that support marine life. surface waters in many low-latitude regions are clear and sunlit with a distinct layer of warmer water above colder, deeper masses. Below, darkness gathers quickly with depth and pressure, rises in quiet, cold plains on the deep seafloor dotted with slow-moving sediments that settle grain by grain. In the skies, the air holds a mixture of gases broadly similar to that of later eras, including nitrogen, oxygen, carbon dioxide, and water vapour, though their exact proportions differ from future values. Oxygen levels are high enough to support active energy-intensive life on land and in the oceans, and the ozone layer in the upper atmosphere filters much of the sun's ultraviolet radiation. High above the surface, jets of wind stream along strong temperature contrasts, while lower down a complex pattern of trade winds, westerlies and polar currents shapes where clouds form and where deserts spread. Thunderstorms rise over warm seas and coastal lands, lightning flickers within tall cloud towers, and gentle persistent rains fall over cooler regions under layered clouds. Volcanic eruptions occur in many places along plate boundaries and hotspots, injecting ash and gases into the air from time to time, but on average the sky remains clear enough for abundant sunlight to reach the ground and the surface of the sea. Across the planet, gravitational and rotational forces continue their constant work. Tides swell and retreat along coastlines as the moon and the sun tug on the oceans, and this regular pulsing helps stir shallow waters and shape coastal environments. The length of the day is slightly shorter than in later ages, because Earth continues to slow its spin over very long timescales, as tidal interactions transfer energy to the orbit of the Moon. Precession and changes in the tilt and shape of the orbit gradually alter the distribution of sunlight over tens of thousands of years, modulating patterns of rainfall and temperature on regional scales. Against this backdrop, the solid Earth slowly cools from within. Heat from radioactive decay and residual formation energy escapes through the crust, while convection in the mantle drives the motion of tectonic plates at the surface. Mountain belts rise where plates collide and are worn down by wind, water, and ice sending sediment toward interior basins and continental margins. Deep within subduction zones, old oceanic crust descends carrying water and carbon-bearing minerals into the mantle, where they may later return to the surface in volcanic gases. Over the span of millions of years, these processes help regulate the level of carbon dioxide in the atmosphere, linking weathering on land, sedimentation in the oceans, and volcanic outgassing in a long, slow cycle. At this late stage in the Cretaceous, that cycle supports a greenhouse climate rather than an icehouse one, with widespread warmth, high sea levels, and extensive shallow seas. The result is a world that is dynamic yet broadly stable on human timescales, with continents in motion, oceans in circulation, and a warm atmosphere moving energy from low to high latitudes in endless repeating patterns. Within this framework, ecosystems of plants, invertebrates, and vertebrates occupy almost every available environment, from coastal plains and river deltas to interior uplands and open oceans, all shaped by the physical conditions of this warm, high sea level world. Late in the Cretaceous, life covers land, sea, and sky in a wide range of forms that have had tens of millions of years to diversify under warm climates and high sea levels. On the continents, dense forests of flowering plants, conifers and ferns spread across lowlands, foothills, and river plains, with variations that follow moisture, soil, and latitude. In many subtropical and temperate regions, tall flowering trees form layered canopies, their branches carrying leaves, seeds, and fruits that feed insects and vertebrates. Beneath these upper layers, shrubs, smaller trees, and ground ferns fill the lower levels, while mosses, fungi, and leaf litter cover the forest floor in a soft, uneven carpet. Along the banks of rivers and lakes, thickets of horsetails, cycads, and other moisture-loving plants stand in bands that follow the water, helping to stabilize sediments and providing shelter for animals that move between land and freshwater. Farther inland, where climates grow drier woodlands and open habitats with scattered trees, give way to areas of low shrubs and hardy plants adapted to less frequent rainfall. In tropical belts where warmth and moisture are abundant, vegetation is especially lush with high rates of growth and decomposition that cycle nutrients quickly through the system and support dense communities of herbivores and decomposers. Non-avian dinosaurs hold many of the large herbivore and predator roles on land. In coastal plains and river valleys, herds of long-necked sauropods crop from the upper parts of trees, or from tall vegetation, their bodies supported by pillars of bone and muscle that spread their weight over broad feet as they walk across soft ground. In other regions, duck-billed hadrosaurs chew tough plant material with complex dental batteries, turning leaves and stems into usable energy through efficient grinding movements of the jaws. Armored ankylosaurs with heavy tail clubs and horned ceratopsians with broad frills and facial horns move through the same landscapes, their skulls and body armor reflecting long histories of interaction with large predators. These herbivores in turn support populations of theropod carnivores. Among them, in parts of what will become North America and Asia, large tyrannosaurids stand as dominant terrestrial predators with massive skulls, powerful jaws and limb proportions that allow bursts of speed over short distances. Smaller predatory dinosaurs, some with feathers and agile builds, hunt small vertebrates or scavenge from larger kills, filling roles that overlap with those of later mammalian carnivores in terms of diet and behavior. In many ecosystems, small mammals already live alongside dinosaurs. These mammals differ from later familiar forms, but they occupy diverse roles as insect eaters, omnivores, and small herbivores. Many are active mainly at night or at dawn, and dusk, their patterns shaped by competition with larger animals and by predation pressure from reptiles and birds. They burrow into soils and sediments, climb shrubs and low trees and forage in leaf litter, feeding on insect seeds and other small food sources. They remain modest in size compared with large dinosaurs, but they show considerable diversity in skull and tooth shape, reflecting varied diets and ways of life. Birds descended from small feathered theropod dinosaurs share the skies with flying reptiles and also live on the ground and in trees. Some bird lineages already show specializations towards strong flapping, flight perching, or aquatic feeding with feathers that provide both insulation and aerodynamic surfaces. Teeth remain in the jaws of many forms, though some lineages have already reduced or lost them, and beaks of different shapes help birds exploit seeds, insects, or aquatic prey. Visual displays and vocal calls form part of the sensory environment of forests, coasts, and open water, as birds defend territories, attract mates, or signal alarm. Pterosaurs, the flying reptiles, occupy a different set of aerial roles. Large pterosaurs with wingspans of many meters soar along coasts and over inland seas, using rising air currents along cliffs and warm thermals over land to stay aloft with minimal effort. Their elongated jaws and pointed teeth suit them to catching fish or other small prey near the water surface. Smaller pterosaurs hunt insects or fish their wing membranes, adjusting to fine changes in airflow as they bank and turn above forests, wetlands, and shorelines. Both birds and pterosaurs make use of the structure of late Cretaceous landscapes, using cliffs, trees, and shorelines as roosts and nesting sites. In freshwater systems, rivers meander across broad floodplains, depositing sediment during floods and shifting their channels over time. Within these waters, fish, amphibians, and invertebrates form food webs that link closely to the surrounding land. Crocodiliform reptiles lie in wait along the edges of rivers and lakes, their bodies adapted to both water and land with powerful tails for swimming, and jaws suited to seizing prey that comes within reach. Turtles, some freshwater and some terrestrial, graze or scavenge, and move between water and land as seasons and life stages require. Amphibians such as frogs and salamander relatives live in and around these waters, their life cycles tied to moist environments. Insects are abundant in almost every terrestrial environment. Beetles, wasps, ants, butterflies, moths, and many other groups feed on plants, each other, and decaying material. Some insects pollinate flowering plants, forming mutualistic relationships that influence the spread and diversification of both partners as pollen passes between flowers and seeds develop. Others bore into wood, graze on leaves, or live in soil and leaf litter, helping to break down organic matter and recycle nutrients back into forms that plants can use. Their small bodies form a crucial link in food chains, transferring energy from plants to larger animals such as birds, small dinosaurs, and mammals. In the oceans, high sea levels create extensive shallow shelves and interior seaways, where sunlight can penetrate to the seafloor. These regions host communities of corals, mollusks, kynoderms, and other invertebrates that build shells or skeletons from dissolved minerals. On some shallow seafloors, shell beds and carbonate platforms accumulate, recording the presence of countless individual organisms over time in slowly thickening layers. In slightly deeper waters, planktonic organisms drift in the upper, sunlit layer. Photosynthetic plankton, including various algae and other microscopic producers, use sunlight-dissolved nutrients and carbon dioxide to build organic matter. They support herbivorous zooplankton, which in turn feeds small fish, larger invertebrates, and juvenile stages of many species. This plankton-based food web provides much of the primary energy input for open ocean ecosystems, linking surface light to deeper waters through sinking particles and migrating animals. Larger marine reptiles occupy roles similar to those of modern whales and large predatory fishes. Mosasaurs with long bodies and powerful tails cruise through open waters and along continental margins, hunting fish, squid like cephalopods and other reptiles. Plesiosaurs with long necks or with broader, shorter necks swim with limb-like flippers, capturing prey in surface waters or at moderate depths. These reptiles share the oceans with sharks and bony fishes that have already diversified into many forms, from swift open ocean hunters to bottom dwellers, adapted to feeding on invertebrates in or on the seafloor. Coastal and nearshore ecosystems show strong ties between land and sea. River deltas deliver sediment nutrients and organic matter from the continents into interior seaways and margins of the great oceans. Vegetation along shorelines, including tree-like plants, tolerant of salt or frequent flooding, stabilizes banks and offers sheltered habitats for juvenile fishes, invertebrates, and small tetrapods. Tidal flats, salt marshes, and lagoons support communities of burrowing organisms, filter feeders, and wading animals that exploit the alternating exposure and submergence with each tide. Climate patterns in the late Cretaceous vary across the globe but generally remain warm. Some regions experience pronounced wet and dry seasons, shaping when plants grow, flower, and shed leaves, and when animals migrate, breed, or enter periods of reduced activity. Other regions near coasts or under persistent oceanic influence enjoy more uniform conditions with fewer extremes of temperature or rainfall. At high latitudes, extended periods of daylight in summer and darkness in winter still occur because of Earth's tilt, but temperatures remain higher than in many later times, allowing forests and diverse animal communities to persist far from the equator. Fire plays a role in many terrestrial ecosystems. In regions with seasonal dryness, lightning ignites vegetation, clearing patches of forest or woodland and creating mosaics of habitat at different stages of regrowth. Some plants show traits that help them survive or even benefit from occasional fires, such as thick bark, the ability to resprout, or seeds that germinate in open sunlit soil. Over time, such disturbances influence which species dominate particular landscapes, and how nutrients circulate between living biomass and soil. Under this climatic and ecological framework, evolutionary trends continue. Some dinosaur lineages evolve more specialized teeth, limbs, or crests that reflect particular diets, displays, or behaviors. Some bird lineages explore new niches in water trees or open ground. Mammals diversify quietly in size, shape, and ecological role, even while remaining in the shadow of larger reptiles in terms of biomass and visibility. Plant communities respond to both climate and herbivory, with flowering plants expanding their presence in many regions and forming new partnerships with insects and vertebrates. Genetic change accumulates generation by generation, not directed toward any goal, but continually exploring the range of forms that can survive and reproduce under late Cretaceous conditions. Viewed across the entire planet, the result is a biosphere that is rich, complex, and dynamic, with food webs linking microscopic producers to the largest predators, and with feedbacks between climate geology and life that play out over timescales from seasons to millions of years. Beyond late Cretaceous Earth, the solar system holds large populations of small bodies that circle the Sun along with the major planets, forming long-term reservoirs of potential impactors. The planets follow nearly stable orbits that change only slowly over immense spans of time, but the paths of smaller bodies are more easily disturbed by gravitational encounters, collisions, and subtle forces. These small bodies include asteroids, comets, and icy fragments left from the formation of the planetary system, and they occupy regions that differ in composition, typical orbit, and long-term behavior. Together they provide the material that occasionally crosses the paths of planets and produces impacts on their surfaces. The most prominent collection of rocky small bodies lies in the main asteroid belt between the orbits of Mars and Jupiter. In this broad donut-shaped region, countless asteroids travel around the Sun, along paths that are roughly aligned with the planetary plane. Their sizes span a wide range from objects only meters across to bodies hundreds of kilometers in diameter. Many asteroids are irregular in shape, shaped by collisions and fragmentations over billions of years, rather than by self-gravity into perfect spheres. Their surfaces are darkened by space weathering coated in regolith made of broken rock and dust that has accumulated after repeated impacts by smaller pieces. The bulk compositions of asteroids vary. Some are rich in silicate minerals more like ordinary rock. Others contain high proportions of metal with dense mixtures of iron and nickel. Still others are carbon-rich, containing primitive material that has changed little since the early solar system, including complex carbon compounds and volatile-bearing minerals. These compositional differences reflect where and how they formed in the early protoplanetary disk, as well as subsequent heating and differentiation. In the main belt, the story of each asteroid is one of long-term collisional evolution. Over time, orbits cross impacts shatter larger bodies, and fragments spread out along similar paths. Families of asteroids with related orbits and compositions trace back to ancient breakups, each group representing the scattered remains of a once larger parent body. Smaller fragments created in such events can drift more easily under subtle forces, including the gentle push of absorbed and re-emitted sunlight that alters their orbits over millions of years. This thermal effect acting continuously can move small objects into different regions of the belt, where gravitational resonances with planets, especially Jupiter, become important. Within the belt and near it, there are locations where the gravitational pull of Jupiter and the repeating timing of orbital periods create resonances. In these zones, an asteroid may complete a simple numerical ratio of orbits for every orbit Jupiter makes around the Sun. At such resonances, small gravitational nudges accumulate, gradually changing the asteroid's orbital eccentricity or inclination. In some cases, this process can increase the elongation of an orbit enough that it crosses the paths of inner planets, including Mars and Earth. Over very long intervals, these resonances act as efficient pathways that can remove objects from the main belt and feed them into the inner solar system as planet-crossing asteroids. Beyond the asteroid belt, the outer solar system holds further reservoirs. In regions beyond the orbit of Neptune lies the Kuiper belt, a population of icy bodies that includes dwarf planets and many smaller objects. These bodies contain mixtures of water ice, frozen gases, and rock, and they follow orbits that range from relatively circular to markedly elliptical and inclined. Some members of this population can be perturbed inward through gravitational interactions with the giant planets, especially Neptune evolving into orbits that bring them closer to the Sun as what are known as short-period comets. As these comets move inward, sunlight heats their surfaces, causing ices to sublimate and release gas and dust that form surrounding comas and tails. The visible display of a comet with its bright nucleus and long tail is thus a temporary manifestation of volatile loss. The underlying nucleus itself remains a small irregular solid body, and when its orbit crosses that of a planet, it can also pose an impact hazard. On even larger scales far beyond the Kuiper belt, a roughly spherical cloud of icy bodies is thought to surround the solar system at great distances. This distant reservoir, known as the Oort cloud, contains countless small icy nuclei residing at distances many thousands of times farther from the Sun than Earth is, over extremely long timescales. Passing stars, giant molecular clouds, and the tidal influence of the Milky Way galaxy can disturb the orbits of these bodies. Some are nudged inward on elongated paths that bring them into the inner solar system, as long-period comets approaching the Sun from many different directions rather than confined to the planetary plane. Although each individual object in the Oort cloud has a very low chance of entering the inner solar system in a given span of time, the large overall population means that such entries still occur on geological timescales. Closer to the planets, small populations of asteroids share or approach the orbits of specific worlds. Near Earth, so-called near-Earth asteroids follow orbits that cross or come close to that of the planet. These objects represent a transient population. Many have been delivered from the main belt through resonances and thermal drift, and over time they are removed by collisions with planets or the Sun, or by being ejected from the inner solar system. Their orbits occupy a complex web of paths, some of which intersect Earth's orbit at various angles and distances. In the present configuration of the solar system, the statistical likelihood of impacts over long time scales is shaped by the distribution and evolution of these objects. The gravitational influence of the giant planets, especially Jupiter and Saturn, plays a central role in governing how material moves between these reservoirs and the inner worlds. Jupiter's large mass allows it to scatter, passing comets and asteroids onto new trajectories, either ejecting them into interstellar space or redirecting them toward the Sun. At the same time, Jupiter's presence helps shape the architecture of the asteroid belt itself, carving gaps in the distribution of orbits through resonances and altering the outcome of collisions by changing the velocities at which objects meet. The overall outcome is not a simple shield or barrier, but a complex interplay in which the giant planet can both deflect potential impactors away and send others inward. Throughout solar system history, these reservoirs of small bodies have supplied every terrestrial planet with impacts of varying sizes. Many of the scars from these collisions remain visible on airless surfaces such as the Moon and Mercury, where craters of all scales record a long history of bombardment. On planets with atmospheres active tectonics and erosion such as Earth and Venus, craters are erased more quickly, but geological studies show that impacts still occur. Large impact events are rare on human timescales, but more frequent over millions or tens of millions of years, with a distribution in which small impacts are common and very large ones are extremely infrequent. The late Cretaceous Earth, with its warm climates and thriving ecosystems, exists within this broader context of an active small body environment. At any given time, countless asteroids in the main belt continue to orbit in relative stability, while some slowly drift toward resonances that can change their paths. Comets in the outer reservoirs occasionally begin long inward journeys under distant perturbations, and near-Earth asteroids follow orbits that sometimes bring them inside the orbit of the planet and sometimes outside it. The probabilities that govern these motions are shaped by the underlying gravitational field of the Sun and planets, and by the slow action of non-gravitational forces such as thermal re-emission of sunlight. Over spans of tens of millions of years, individual objects can transition between categories, moving from main belt asteroid to near-Earth object, or from distant icy body to active comet in the inner solar system. These transitions provide a steady though irregular supply of potential impactors. The physical properties of the small bodies influence what happens if they strike a planet. A rocky or metallic asteroid behaves differently from a loose icy comet when it enters an atmosphere or hits a solid surface. Density, internal strength, porosity and velocity all affect the size and shape of the resulting crater, the amount of material excavated and the energy delivered to the atmosphere and crust. The angle of impact and the nature of the target rocks also play significant roles. Across all these factors, the central quantity is the kinetic energy of the incoming body, which depends on its mass and speed. In the inner solar system, typical impact speeds for small bodies colliding with Earth range from several kilometers per second to tens of kilometers per second, ensuring that even modest-sized objects can release large amounts of energy on contact. In the late Cretaceous, these processes operate as they do at other times in Earth's history. The reservoirs of asteroids and comets continue to evolve under the influences of gravity radiation and internal collisions. Most small bodies complete their orbits without ever approaching a planet closely. Some are broken apart in collisions with other small bodies. Others are slowly nudged onto paths that intersect planetary orbits. Against the long background of these probabilities and mechanisms, the stage is set within the solar system for occasional large impacts on the inner planets, including Earth, as material migrates inward from its long-term reservoirs and sometimes meets a world in precisely the right place and time for a collision to occur. The impactor that strikes late Cretaceous Earth at the end of the Cretaceous period leaves no intact body behind, yet its character does not vanish without trace. Its substance melts, vaporizes and mixes with target rocks and atmosphere, but chemical and physical clues remain in tiny fragments, altered minerals and the geometry of the crater. From these clues, scientists build a picture of what kind of object it is and from where in the solar system it most likely comes. The emerging view points to a rocky carbon-rich asteroid, rather than an icy comet, a body that once belongs to the main asteroid belt, before its orbit shifts toward Earth. Meteorites that fall in the present era help set the framework for understanding such an object. When small fragments of asteroids survive passage through the atmosphere and land on the surface, they bring samples of different asteroid types within reach of laboratory study. Researchers sort these meteorites into broad classes based on mineral content texture and the presence of metal volatiles and complex carbon compounds. One important group is known as carbon-rich chondrites, primitive stony meteorites that contain a high fraction of carbon-bearing material and small rounded grains called chondrules that formed early in the solar system. These meteorites preserve a mix of minerals and organic compounds that records conditions in the protoplanetary disk before larger bodies fully separate into metal cores and silicate mantles. When the chemical makeup of material associated with the Chicxulub impact is measured, it shows patterns similar to those seen in certain carbon-rich chondrites, rather than in metal-rich or purely rocky types. Proportions of elements such as iridium-nickel and other siderophile elements which have a strong tendency to bond with metal stand out as particularly useful. These elements are rare in Earth's crust because most of them sink into the core during early differentiation, but they remain relatively abundant in undifferentiated asteroids. An enhancement of such elements above typical crustal levels signals the addition of extraterrestrial material. In the case of the Chicxulub event, the concentration ratios of iridium and other elements in impact-related material match those expected from a carbon-rich asteroid of a particular kind, rather than from an icy comet nucleus or a metal-dominated body. The mineral structure of tiny spherules and shocked grains associated with the impact also carries information about the impactor. During the collision, part of the projectile and part of the target rock melt, and are thrown out as droplets that cool into small glassy spheres and fragments. The chemistry of these droplets combines contributions from both the impactor and the target rocks. By separating those contributions through careful analysis and modelling, researchers estimate the relative proportions of projectile and target material, and thus constrain the average composition of the incoming body. Certain isotopic ratios, for example in chromium, further narrow the range of possible source populations by matching the fingerprints of specific meteorite classes. Although detailed descriptions of the boundary deposits belong to later parts of the story, it is within such microscopic particles and altered minerals that the signature of the impactor's composition resides. Spectral observations of asteroids provide another line of evidence. When sunlight reflects off the surfaces of asteroids, their mineral content affects the colours and patterns seen in the reflected light. Telescopes equipped with spectrometers measure how brightness changes with wavelength, revealing absorption features that correspond to particular minerals and carbon-rich compounds. Asteroids in the main belt fall into several spectral groups, some matching the properties of carbon-rich chondrites. By comparing the inferred composition of the Chicxulub impactor with the properties of these asteroid classes, scientists identify likely matches in the outer part of the main belt where many dark carbon-rich asteroids dwell. Numerical models of orbital evolution add a dynamical perspective. These models simulate the paths of many hypothetical asteroids as they experience gravitational tugs from planets and the small but persistent effects of thermal forces over tens or hundreds of millions of years. They track how objects drift in semi-major axis, eccentricity and inclination, and how they enter resonances that can drive them into planet-crossing orbits. When the distribution of near-Earth asteroids and the observed impact rate on Earth are taken into account, the models indicate that large impacts by carbon-rich asteroids of a size similar to the Chicxulub impactor most likely originate from the outer main belt where appropriate source populations are abundant and pathways into resonances are available. In this view, The impactor begins as a fragment of a larger parent body in that region, perhaps created by an ancient collision that yields a family of related asteroids sharing similar orbits and compositions. Over long intervals, the fragment's orbit slowly changes through thermal drift until it reaches a resonance with Jupiter or Mars. Once their repeated gravitational nudges increase the eccentricity of its orbit, stretching it until it crosses the paths of the inner planets. At some point, the evolving orbit intersects that of late Cretaceous Earth, at a particular distance from the Sun, setting the stage for a possible collision when both bodies reach the crossing point at the same time. The estimated size of the Chicxulub impactor also helps refine its nature. From the diameter and depth of the crater combined with scaling relationships derived from modeling and from other impact sites, scientists infer that the incoming body has a diameter of roughly 10 to 15 kilometers. An object of this scale carries enormous kinetic energy at typical impact speeds in the inner solar system, sufficient to excavate a crater more than 150 kilometers across, and to launch material far beyond the immediate region. Such a size is common among larger main belt asteroids, but less typical for comets that approach from the distant reservoirs, at least in terms of those observed passing near Earth. The impact angle and speed are harder to recover, but modelling suggests values within the range expected for asteroidal impacts, rather than requiring unusually high velocities more characteristic of some long-period comets. Alternative hypotheses have proposed that a long-period comet from the distant outer reservoirs might be responsible, pointing to the existence of large cometary bodies and their occasional incursions into the inner solar system. However, when the full suite of geochemical data crater characteristics and dynamical models are considered together, the balance of evidence favours a carbon-rich asteroid from the main belt. The elemental ratios, isotopic signatures, and inferred density align more closely with carbon-rich chondritic material than with the mixtures of ice and dust typical of cometary nuclei. Probability estimates based on the known populations of large asteroids and comets also suggest that large asteroidal impacts of this kind are more frequent over hundreds of millions of years than impacts by very large long-period comets. Despite these lines of evidence, some uncertainty remains. The precise parent body of the impactor is not identified, and no present-day asteroid can be pointed to as the direct source. Over tens of millions of years, families of asteroids spread out in orbital space, and fragments collide, break, or are removed from the system, erasing simple links. Processes that alter surfaces such as space weathering and small impacts can also change spectral properties over time, complicating attempts to match meteoritic and telescopic data exactly. Isotopic signatures, while powerful, are compared with a sample of meteorites that may not capture the full diversity of small bodies. As a result, the origin story remains a probabilistic reconstruction rather than a direct identification. Nevertheless, the convergence of independent approaches gives a coherent picture. Chemical analyses point toward a carbon-rich primitive asteroid. Spectral classifications and dynamical pathways suggest an origin in the outer part of the main asteroid belt, where many such bodies reside, and from which resonant routes to Earth crossing orbits exist. Scaling relationships between crater size and impactor properties support a rocky object of moderate density and significant size. Within this framework, the Chicxulub impactor appears as one fragment among many, in a long-lived population of asteroids, its path shaped by slow forces acting over immense timescales. It travels unnoticed for most of its existence, one dark body among countless others, until cumulative changes in its orbit eventually place it on an intersecting course with late Cretaceous Earth, linking its distant origin to a specific point in space and time, where planet and small body meet. The fragment that will one day strike late Cretaceous Earth begins its independent existence long before the impact as a piece of rock liberated from a larger parent body in the outer part of the main asteroid belt. In that early collisional event, stresses exceed the strength of the parent fractures propagate through its interior, and multiple pieces fly apart along similar paths around the Sun. Some fragments are large enough to maintain irregular shapes under their own weak gravity, others are much smaller collections of boulders and dust that move together as loose aggregates. Among these fragments is the body that will eventually become an impactor. At first, its orbit closely matches that of its parent, a roughly circular path between Mars and Jupiter that remains well separated from the orbits of the inner planets. Life on Earth evolves and spreads during this time without knowledge of the fragment's existence, while the fragment itself circles the Sun again and again, a dark rock in a belt filled with other small worlds. Over countless revolutions, small forces begin to alter its path. Sunlight warms one side of the rotating body more than the other, and as the heated surface cools and re-radiates energy back into space, it produces a tiny but persistent thrust. This thermal reaction, integrated over millions of years, can nudge the orbit inward or outward by small amounts, depending on the direction and speed of rotation and the details of the surface. For a body several kilometers across, the change over a single orbit is negligible. But over tens of millions of years, the cumulative effect can shift the semi-major axis of the orbit noticeably. The fragment also feels gravitational tugs from neighboring asteroids during distant flybys from the passing pull of Mars and Jupiter, and from subtle variations in the mass distribution of the asteroid belt as a whole. These influences superimpose slow oscillations in orbital elements such as eccentricity and inclination onto the long-term drift driven by thermal forces. The outcome is a gradual migration through orbital space, a slow walk across the wide lanes of the belt rather than a sudden leap. As the fragment's orbit moves, it approaches regions where resonances become important. In these zones, the period of the asteroid's orbit locks into a simple, numerical relationship with that of a planet, most often Jupiter. Each time the asteroid passes a particular point in its orbit, Jupiter occupies nearly the same relative position, and their gravitational interaction repeats with a consistent phase. On short timescales, each encounter produces only a modest change, but over long spans, these repeated tugs can alter the shape of the orbit significantly. The semi-major axis may remain nearly steady within the resonance, but the eccentricity can increase, transforming a more circular path into an elongated one that brings the asteroid closer to the Sun at one end of its orbit and farther away at the other. The inclination can also change, tilting the orbital plane relative to that of Earth and the other inner planets. Within such a resonance, small differences in starting conditions lead to diverging paths, and the motion enters a chaotic regime where long-term predictions for individual objects become difficult even if the overall statistical behavior remains well defined. For many asteroids, passage through a resonance eventually leads to removal from the main belt. Some are flung outward, their orbits stretched and raised until they cross those of the giant planets, or are ejected into interstellar space. Others are driven inward, their perihelia dipping toward the orbits of Mars, Earth, and Venus. The fragment that will form the Chicxulub impactor follows one of these inward pathways. As its eccentricity grows, the closest point of its orbit to the Sun moves inward into the region of the inner solar system, while the farthest point remains in the asteroid belt. At first, its perihelion may cross the orbit of Mars, making close approaches to that planet possible. Mars, though small compared with Jupiter, can still deflect the fragment during near passes, tweaking its orbital elements by small amounts that accumulate over time. These encounters, combined with continuing resonant forcing and thermal drift, gradually reshape the orbit until it crosses Earth's path as well, the fragment has now become a near-Earth asteroid, part of a population whose members share the property that their orbits bring them close to or across the orbit of Earth. In this stage, its dynamical lifetime is limited. Near-Earth objects are removed relatively quickly on geological timescales, through collisions with planets or the Sun, ejection from the inner solar system, or disruption in further collisions with other small bodies. Typical survival times in such orbits span a few million years to a few tens of millions of years, much shorter than the age of the solar system. For most objects, this phase ends without any collision with Earth, as they pass by at safe distances or are diverted elsewhere. For a small subset, however, their paths and the positions of planets align such that an impact eventually occurs. Once the fragment's orbit intersects that of Earth, each revolution around the Sun presents an opportunity for a close passage. Whether that passage results in a distant flyby, a closer gravitational encounter, or an impact depends on the relative timing and three-dimensional geometry when both bodies reach the vicinity of the crossing point. From the perspective of celestial mechanics, this is governed by the periods of the two orbits, the orientation of the asteroid's ellipse and the precession of its line of apsides and nodes. From the perspective of time on Earth, it means that over many thousands or millions of years the fragment passes near the planet multiple times at varying distances. Some of these close approaches can themselves modify the orbit, as Earth's gravity slightly bends the path, changing future perihelion distances, nodes, and encounter geometry. Under certain conditions, a single close passage can steer the asteroid through a narrow corridor in space that sets up an impact on a later orbit, a concept known from studies of gravitational keyholes. In other cases, no such specific corridor is needed. Instead, the slow evolution of orbital elements under multiple influences eventually brings the asteroid onto a trajectory that intersects Earth's position at a future time. Throughout this evolution, the fragment remains physically much the same. Surface impacts by micrometeoroids roughen its regolith exposure to solar wind, and cosmic rays alters the outermost layers of minerals, and thermal stresses crack rocks on its surface, but its bulk, structure, and composition remain those of a primitive carbon-rich asteroid. Its rotation period and axis orientation may change due to small torques from asymmetric radiation of heat or from impacts by smaller bodies, and these changes can adjust the direction and magnitude of thermal drift, sometimes pushing the object in and out of resonances or altering how quickly it moves through them. These feedbacks between rotation thermal forces and orbital changes add complexity to the path, but still operate within the established rules of celestial mechanics. On timescales relevant to the late Cretaceous, what matters is that the fragment, once a distant and unremarkable member of the main belt, now spends its time in an orbit that regularly takes it through the region occupied by the inner planets. Each close approach to Earth offers an opportunity for the orbit to be reshaped slightly, or for a collision to occur. Most such encounters would in general end with the asteroid and Earth passing safely by one another, separated by large distances in space. Eventually, however, one particular configuration in space and time leads to alignment between the asteroid's position and Earth's position at the crossing point of their orbits, so that the small body does not pass at a distance, but meets the planet at a specific place and moment in its long journey around the Sun. On the orbit that leads to impact, the fragment now moves as a near-Earth asteroid, whose elongated path around the Sun crosses the orbit of late Cretaceous Earth at a specific point in space. Each year, Earth travels through this crossing point as it completes its circuit, and each year the asteroid also sweeps through its own orbit, but only when both arrive near the crossing within the same narrow interval of time does a close encounter occur. On previous revolutions, the timing is such that the asteroid passes the crossing either before Earth arrives or after it has moved on, so that the two bodies miss one another by wide margins measured in millions of kilometers. On the approach that matters, the phasing of their orbits has shifted just enough that the positions now align. At a time, some tens of millions of years after the asteroid first becomes a near-Earth object, Earth reaches the point where its orbit intersects that of the fragment, at almost the same moment that the fragment also arrives there, and the small body begins its final approach toward the planet. From a vantage point far above the solar system, this final approach appears as a simple geometric crossing. Earth continues along its nearly circular path, carrying continents, oceans and atmosphere around the Sun in a nearly constant pattern. The asteroid approaches on a more eccentric ellipse that dives inward toward the Sun and then swings back out again, its track tilted slightly with respect to the plane of Earth's orbit. As the two paths intersect, Earth's much greater mass slightly warps the local gravitational field, bending the asteroid's trajectory inward in a process known as gravitational focusing. Instead of passing by in a straight line relative to Earth, the asteroid's path curves toward the planet, increasing the likelihood of impact for any object that comes within a certain distance of its center. The asteroid's speed relative to the Sun at this point reflects a balance between the gravitational pull of the star and the energy of its orbit, and its relative speed, with respect to Earth, arises from the combination of their motions along their respective paths. The result is an approach velocity that in typical cases for such objects lies in the range of several tens of kilometers per second. Long before the asteroid nears Earth, its motion has been determined by this orbital energy and by the distribution of mass in the solar system. No new forces arise on the final orbit aside from the gradual increase in Earth's gravitational influence as the distance shrinks. Day by day and then hour by hour, the separation decreases first by large fractions of the Earth-Moon distance, and then by smaller and smaller portions as the asteroid descends a gravitational slope toward the planet. Within this framework, the asteroid itself remains physically modest in appearance. It is an irregularly shaped object, perhaps 10 or more kilometers across, far too small to pull itself into a sphere, with a surface coated in a mixture of broken rock fragments, dust, and compacted regolith. Craters of various sizes pockmark its surface from earlier impacts, with smaller bodies, and boulders lie scattered where past collisions have fractured bedrock. The overall colour is dark, reflecting the carbon-rich composition inferred from later geochemical evidence, so that in visible light it reflects only a small fraction of the sunlight that falls on it. The body rotates as it travels, turning slowly or moderately around an axis set by earlier collisions and torques, so that any given point on its surface experiences cycles of day and night on timescales of hours or longer. As it approaches, the balance of radiation and thermal emission continues to act, but over the short timescale of the final orbit, such non-gravitational forces have negligible effect on its path. The gravitational pull of Earth now dominates the motion, aside from the central attraction of the Sun, and the orbit bends to intersect the planet's surface. At large distances, the asteroid lies well outside the orbit of the Moon, and its presence has no perceptible effect on conditions at Earth's surface. Weather patterns continue to develop under the influence of solar heating rotation and the distribution of land and sea. Tides rise and fall under the familiar combined gravities of the Moon and the Sun. Dinosaurs, marine reptiles, birds, mammals, plants and plankton carry out their daily cycles, as they have for countless generations, responding to local changes in light, temperature and moisture, not to distant celestial mechanics. The asteroid is too small and too faint to be visible against the glare of daylight, or even to stand out easily in the night sky without instruments, and there is no change in the regular patterns of the stars that would signal its approach to any animal or observer on the ground. Within a region around Earth known as the Hill Sphere, where the planet's gravity dominates over that of the Sun for the purposes of holding moons, the asteroid's trajectory bends more noticeably. Once it enters this zone at a distance of roughly 1.5 million kilometers, the relative speed and direction of its approach combined with the gravitational field define a specific impact parameter and thus a specific impact point on the rotating planet. Because Earth turns once every roughly 24 hours, any point on its surface under the crossing point of the asteroid's original orbit moves through a broad band where an impact could fall, and the actual site is determined by the precise timing of the encounter. At the moment when the asteroid has descended to within the distance of the Moon's orbit, the geometry of the situation is essentially fixed. The relative velocity vector and position vector define a path in 3 dimensions that terminates at a single region on the surface, unless modest perturbations intervene, and at this scale there are no further massive bodies close enough to provide such perturbations. The asteroid's path now intersects the atmosphere above what will one day be called the Yucatán Peninsula and the adjacent shallow seas of the Proto-Caribbean region. The impact angle measured between the incoming trajectory and the local horizontal plane at the impact site sets another crucial parameter that influences later crater shape and ejecta distribution. Estimates based on modelling and the symmetry of the crater suggest a moderately oblique impact, rather than a purely vertical one, with the asteroid arriving at a steep but not straight downward angle from the sky. This angle, combined with the asteroid's size, density and speed, determines the depth to which kinetic energy will penetrate into the crust and the pattern in which material will be ejected, but at this stage it remains simply a geometric relation between the incoming path and the surface. In the hours before atmospheric entry, the asteroid crosses the orbit of the Moon and continues inward, passing through regions of space where in other contexts artificial satellites would later circle the planet. Its apparent motion across the sky as seen from Earth speeds up as the distance shrinks, but until the final minutes before entry, it remains a faint point of light outshone by the Sun in daytime, and for most practical purposes by the brighter stars and the diffused light of the Milky Way at night. The only clear record of its approach lies in the equations of motion that much later allow scientists to reconstruct such trajectories in general terms through numerical integration and statistical modelling. At the surface, regional environments around the future impact site show no immediate warning in physical terms. The shallow seas overlying the carbonate-rich crust of the Proto-Yucatán platform continue to host marine communities adapted to warm, clear waters. Carbonate sediments accumulate grain by grain on the seafloor, building up layers of lime muds, skeletal fragments and chemical precipitates that reflect the steady interplay of biological activity and seawater chemistry. Coastal lowlands, wetlands and inland ecosystems maintain their patterns of growth, reproduction, and death influenced by climate, sea level and tectonics. The gravitational pull of the approaching asteroid is far too weak, even at close distances, to alter tides, trigger earthquakes, or produce any large-scale deformation before impact. The last stages of approach unfold rapidly compared with the long timescales that have led to this configuration. As the asteroid descends through the final tens of thousands of kilometers above Earth, its speed relative to the planet is now dominated by gravitational acceleration toward the surface combined with its initial orbital velocity. The direction remains essentially fixed, determined by the earlier evolution of its orbit and by the precise timing of the encounter. Within minutes it will meet the uppermost layers of the atmosphere at hypersonic speed, and the physical processes governing the entry, including compression of air shock heating and deceleration, will begin to act. up to the boundary where the atmosphere becomes dense enough to interact strongly with the asteroid's bulk. However, the motion has been a largely ballistic fall under gravity, the outcome of a long history of small changes in orbital elements that have brought this particular fragment from a distant region of the main asteroid belt into immediate proximity with Earth's surface at this specific late Cretaceous moment. As the asteroid reaches the outermost traces of Earth's atmosphere above the region that will one day be called the Yucatán Peninsula, its motion remains dominated by its original orbital velocity and by gravitational acceleration toward the planet. The body approaches at a speed of several tens of kilometers per second, far faster than any wind or aircraft in the atmosphere, and the thin gas at high altitude offers almost no resistance at first. Molecules of nitrogen, oxygen, and trace gases drift in the near vacuum space so widely that collisions between them are rare. The asteroid passes through this region almost as if it were empty space. Its path scarcely altered its surface temperature, controlled mainly by the balance between absorbed sunlight, radiated heat, and the small amount of friction generated in this extremely tenuous gas. As the asteroid descends, the density of the atmosphere slowly increases. Molecules become more frequent, collisions between them more common, and the collective behavior of the gas begins to matter. At such high speeds, the asteroid cannot push the air aside gently. Instead, the gas in front of the body compresses abruptly into a thin, intense shock wave. This shock forms slightly ahead of the asteroid's leading surface, creating a region where air is suddenly heated and pressurized as kinetic energy from the asteroid's motion transfers into the gas. Temperatures in this compressed region rise to many thousands of degrees Celsius, hot enough to ionize atoms and strip electrons from molecules, producing a glowing plasma that envelops the front of the asteroid in a luminous sheath. The asteroid itself does not yet contact this gas directly. A narrow gap of lower density air lies between the shock front and the solid surface, a standoff distance set by the balance of forces in the high-speed flow. Within this layer, heat is transported to the asteroid partly by radiation from the hot gas, and partly by conduction and convection in the thinner boundary region. As the body plunges deeper into the atmosphere, the density and pressure of the oncoming air increase rapidly, and the intensity of the shock grows. The rate at which kinetic energy is converted into heat in the gas peaks near altitudes where the product of air density and the square of velocity reaches its highest values, often at tens of kilometers above the surface. For a large, fast-moving asteroid, energy deposition along this path far exceeds that of ordinary meteors. The heated air radiates strongly in visible and infrared wavelengths, and from the ground under clear conditions the entry would appear as an extremely bright source, moving rapidly across the sky, outshining the sun for a brief interval. The light does not come primarily from molten rock shedding from the asteroid's surface, but from the incandescent gases in the shock layer and wake. The asteroid experiences intense heating at its leading phases. Surface materials absorb radiant and convective heat from the surrounding gas, and their temperatures rise far above normal rock temperatures. If the body were much smaller, this heating could cause it to fragment or even to disintegrate fully before reaching the ground, as happens with many incoming meteoroids. In the case of a body around 10 kilometers across, models and experiments indicate that atmospheric drag and heating, while severe, are insufficient to break up or slow the mass significantly before it reaches the lower atmosphere. The asteroid may lose some outer layers through ablation, as molten and vaporized material strips away into the wake, but its interior remains intact, and its speed decreases only modestly compared with the original orbital value. The resulting trajectory stays close to a straight line in the reference frame of the atmosphere, intersecting the surface at a steep angle. The oblique nature of the path influences the pattern of stresses within the asteroid during entry. As the leading side of the body faces the highest dynamic pressure shock-induced stress waves travel through its interior, potentially exploiting any pre-existing flaws, fractures, or weak zones left from its earlier collisional history. Some chunks of rock may detach and trail behind as secondary fragments, each generating its own smaller shockwave and luminous envelope. However, for an object of this scale and composition, most of the mass remains concentrated in a single coherent core until very late in the descent. The lateral spreading of the wake and any fragments contributes to the area over which energy is deposited into the air, but does not prevent the formation of a single dominant impact site. The atmosphere reacts to the intruder in complex ways. Behind the leading shock, a turbulent wake forms filled with vortices, eddies, and mixing layers, as hot gas moves aside and then rushes back to fill the path of the asteroid. In this wake, temperatures and pressures remain high for a short time before relaxing back toward ambient conditions. The disturbance propagates outward as secondary shock waves and pressure pulses that can travel great distances. For a very large impactor, the local atmosphere near the path behaves almost like a fluid, forced aside by a fast-moving solid piston with strong compression and rarefaction. The front shock wave outruns the asteroid itself, moving ahead into previously undisturbed air at roughly the local speed of sound multiplied by a factor that depends on the shock strength. On reaching lower altitudes where air is denser, the shock becomes capable of causing damage at the surface even before the asteroid arrives. Trees, water surfaces, and rock faces directly beneath the path may experience sudden pressure jumps, followed by rapid drops generating gusts and mechanical stresses. Yet this effect remains very brief in time and localized compared with what will follow when the asteroid's kinetic energy is transferred directly into the crust and atmosphere at the point of impact. The depth to which the asteroid penetrates before meeting significant deceleration depends on its density, size, and velocity, as well as on the thickness and structure of the atmosphere at that time. Late Cretaceous air composition and temperature profiles are not identical to modern ones, but the overall column mass of the atmosphere is comparable, and thus the total amount of air the asteroid encounters on its way to the surface is similar. For a body of 10 or more kilometers in diameter, the mass of air displaced along its track is small compared with the mass of the asteroid itself. As a result, the asteroid retains most of its kinetic energy and momentum until it reaches altitudes very near the ground. Only in the final seconds of flight does the air offer enough resistance to slow the body measurably, and even then the deceleration occurs over a relatively short distance measured in a few tens of kilometers or less. The compression of air in front of the asteroid converts a fraction of its kinetic energy into thermal energy in the gas rather than directly in the ground. This preheating of the atmosphere means that by the time the body nears the surface, a column of extremely hot, high-pressure air stretches along its path. The leading edge of this column presses downward, exerting intense forces on the underlying air and surface even before the solid mass arrives. Some models describe how this superheated gas contributes to the formation of a fireball that expands rapidly after impact, adding to the thermal radiation experienced over wide areas. In this entry-focused stage, it is sufficient to note that the atmosphere acquires a large store of energy, and that this energy is concentrated in a narrow region around the trajectory. The angle of entry over the Proto-Yucatán region determines how far the asteroid travels through the denser lower atmosphere before striking the surface. A very shallow angle would produce a long path through thick air, potentially causing more widespread heating along the track, and in extreme cases for smaller bodies allowing the object to skip or fragment. A near vertical path would shorten the transit and concentrate energy deposition more locally. In the case reconstructed for the Chicxulub, impact estimates point to an intermediate steep angle. Under such conditions, the asteroid crosses the dense lower atmosphere in only a few seconds, leaving little time for drag to redistribute its energy before contact with the surface. Throughout this descent, the timescale remains extremely short compared with most atmospheric and geological processes. From the moment the asteroid begins to encounter appreciable air density to the moment of ground contact, the interval may span less than a minute. During this period, no large-scale atmospheric circulation can respond to the disturbance. The winds and pressure systems that shape weather and climate on longer timescales act too slowly to matter. Instead, the behavior of the air is governed by the immediate physics of shockwaves, compressible flow, and heat transfer in a rapidly moving, locally disturbed column. For organisms at the surface, if any were able to perceive the approach directly, the sequence would unfold with very little warning. An extremely bright source would appear in the sky, accompanied by a sudden increase in light, and soon after intense heating and a fast-moving shock wave. However, for many locations away from the direct path, these signals would be delayed or modified by distance terrain and atmospheric conditions. On the scale of the planet, the entry phase is a very local event confined to a narrow corridor through the atmosphere and to the immediate region beneath it, while the rest of Earth still lies temporarily outside the cone of direct disturbance. As the asteroid reaches the last few kilometers above the proto-Yucatán seafloor and adjacent shallow waters, the atmosphere between it and the surface compresses further, unable to escape sideways quickly enough to relieve the pressure. The gas in this final gap becomes extremely hot and dense, and its ability to cushion the impact is limited. The asteroid's speed remains supersonic by a wide margin, and deceleration increases sharply only in the moments just before contact. The front of the body now lies only fractions of a second away from the rocks and sediments that make up the upper layers of the crust in this region. All of the orbital energy accumulated over tens of millions of years of travel around the Sun is about to be delivered in a very short time into a small volume of crust ocean water and atmosphere at the point where the asteroid and Earth's surface meet. At the instant when the asteroid's solid mass meets the uppermost layers of rock and water in the proto-Yucatán region, the long, largely gravitational fall ends, and an extremely rapid transfer of energy into the target begins. The body arrives at a steep angle over a shallow sea that covers a thick platform of carbonate and evaporate rocks, underlain by deeper crystalline basement. Between the descending asteroid and these strata, a column of air is already heated and compressed by the preceding passage through the atmosphere. In the final fraction of a second, this gas is squeezed even further as the asteroid drives it downward, but it cannot escape sideways quickly enough to relieve the pressure. The compressed air acts briefly as part of the impact, adding to the pressure at the point of contact, yet it is only a minor contributor compared with the direct momentum of the asteroid and the strength of the shock that now moves into the crust. When the leading surface of the asteroid reaches the interface between ocean and seafloor, neither the water nor the rock remains in an ordinary state. Under the extreme pressures generated in these first instants, both the projectile and the target behave more like dense fluids than rigid solids. A strong shock wave forms at the contact surface and propagates outward and downward into the crust and upward into the asteroid. Within microseconds, pressures in the shocked zone rise far above those found naturally anywhere in Earth's interior, and temperatures climb to many thousands of degrees Celsius. Mineral structures that are stable under normal conditions collapse or transform into high-pressure phases. Bonds within crystals are distorted or broken, and both target and projectile materials begin to melt and vaporize. The asteroid itself does not bore a neat tunnel into the crust. Instead, as the shockwave runs through it from the front toward the back, the entire body is decelerated abruptly. Its kinetic energy accumulated over tens of millions of years of orbital motion is converted within a tiny fraction of a second into internal energy of rock and gas. The bulk of the asteroid is compressed, heated, and effectively shredded, mixing with equally transformed target material in a violently disturbed volume at and just below the surface. In this region, densities, pressures, and temperatures all reach extremes that push ordinary rock far outside its usual field of stability. As the shock passes, the compressed material behind it attempts to expand, creating a complex pattern of rarefaction waves and fluid-like flow. Near the point of impact, a large mass of rock sediment and seawater is driven downward and outward, while another mass is accelerated upward. The downward-driven component excavates a rapidly forming cavity in the upper crust, while the upward-moving material begins to rise as a plume of superheated vapor melt and entrained debris. This rising mass forms what is often described as a fireball, a roughly hemispherical volume of incandescent gas and tiny particles that expands above the impact site. Its temperature is so high that it radiates intense visible ultraviolet and infrared light, bathing the surrounding region in a glare far more intense than ordinary sunlight. The composition of this fireball reflects the materials present at the impact site. Vaporized seawater contributes large amounts of water vapor. Carbonate rocks, once stable accumulations of marine shells and chemical precipitates, decompose under the heat-releasing carbon dioxide and other gases. Evaporate deposits that contain sulfur-bearing minerals break down as well, sending sulfur dioxide and related compounds into the hot mixture. Silicate rocks from both the crust and the asteroid contribute atomized and molten mineral components that cool into glassy droplets and fine dust. The proportions of these components vary with depth and position in the target, but together they load the expanding plume with a complex blend of vapors and tiny solid or liquid particles. At the same time, a shock wave runs through the ocean above the impact point. In the shallow water directly over the target, the distinction between sea and crust blurs as both are vaporized or strongly shocked. Slightly farther away, the water column transmits pressure as a series of intense pulses that travel outward from the impact center through the surrounding seas. Within the crust, the primary shock front moves outward in a roughly hemispherical pattern, declining in strength with distance yet still carrying great energy near the center. Rocks at depth are compressed elastically at first and then plastically, depending on their composition and prior state. The intense compression generates seismic waves that spread through the crust and mantle, and these waves deform rocks over a wide region. Close to the impact, however, the distinction between seismic motion and fluid motion becomes less clear as the rock near the surface is molten or fragmented enough to flow on very short timescales. At the surface and just above it, the expanding fireball interacts with the surrounding atmosphere. The hot gas and vapor push outward, driving a blast wave ahead of them. This blast wave is a zone of very high overpressure that moves rapidly away from the impact site through the air, flattening or stripping any structures or vegetation in its path and sweeping loose material outward. The front of the blast outruns much of the material in the plume itself, delivering a sharp, intense pulse of pressure and wind across the landscape surrounding the newly forming cavity. In the earliest moments, this blast is strongest over the area nearest the crater and weakens with increasing distance, but it remains one of the most immediate manifestations of the energy release at ground level. Behind the blast front, hot gases from the fireball radiate heat to the ground. Within a region near the impact, thermal radiation is intense enough to raise surface temperatures, rapidly charring or igniting combustible material. even at greater distances where direct mechanical effects of the blast have weakened the light and heat from the expanding plasma, may still be strong enough to affect surface conditions. The exact radius of these effects depends on the detailed energy partitioning between mechanical and thermal components, and on atmospheric conditions, but the central point remains that a large fraction of the asteroid's kinetic energy is now present in the form of hot expanding gases that both push on the air and radiate outward. Within the body of the Earth, the passage of the shockwave leaves distinctive marks in the rocks. Minerals subjected to the extreme pressures and temperatures develop planar deformation, features narrow, closely spaced bands of altered structure within crystals. Quartz grains acquire parallel lamellae. Feldspars may transform into high-pressure forms. Some of the shocked and melted material is ejected from the growing cavity along ballistic paths, while some remains within the target zone where it cools and solidifies into impact melt sheets and breccias rocks made of broken fragments cemented together. In the contact and early excavation phase, these materials are still in motion, their trajectories and final locations not yet fixed. The entire sequence from initial contact to the establishment of a fully developed shock field and fireball takes place over a remarkably short interval. The time between the first touch of the asteroid on the seafloor and the moment when most of its mass has been decelerated to rest, relative to the local crust, is measured in seconds or less. During this brief period, the distinction between projectile and target essentially disappears. The incoming body becomes part of the target, its identity preserved only in chemical signatures and in the added energy it brings. From this point onward, the evolution of the system is governed less by the motion of a single solid object and more by the fluid and plastic behavior of shocked rock vapor and melt, responding to gravity and pressure gradients. A deep hot zone beneath the impact site now contains a mixture of molten and partially molten material surrounded by severely fractured rock. Above, the expanding plume and blast wave continue to grow, carrying energy into the atmosphere and into the surrounding landscape, while within the crust the conditions created in these first instants begin to drive the excavation of a large transient cavity in the upper crust. In the seconds after the initial contact, the impact site enters what is known as the excavation stage, a brief interval in which the energy delivered by the asteroid reshapes the upper crust into a deep, unstable cavity. The shock wave that forms at impact has already propagated outward and downward, compressing and heating rock and water into a mixed zone of melt and vapor. As the shock front passes, a rarefaction or release wave moves back through this compressed material and allows it to expand. Near the surface, this expansion drives large masses of rock and sediment away from the impact point, both upward and outward, while the underlying volume, now depleted and weakened, collapses downward. The combined effect is to carve a rapidly growing bowl into the crust, the transient crater, which is far deeper and narrower at first than the crater that will remain once the system settles. Material that is excavated from this forming cavity does not simply pile up nearby. Much of it is launched on ballistic trajectories thrown into the air at speeds of several kilometers per second. Blocks of rock, fragmented sediment and droplets of molten material rise in an expanding curtain that moves up and out around the impact point. The curtain thickens as more material joins it, and then thins as gravity slows and reverses the motion of its upper parts. Some of the ejecta falls back into the growing cavity, contributing to the chaotic interior fill. Some lands on the surrounding surface in a thick, coarse blanket near the rim, and in progressively thinner, finer layers farther away. The details of the ejecta pattern depend on the impact angle, the structure of the target, and the mechanical properties of the rocks, but in all cases the excavation lifts a large volume of material out of the cavity and deposits it across a wide area. Within the target rocks, the excavation stage produces distinctive zones. Closest to the impact center, a volume of rock has been so heavily shocked and melted that it flows as a thick pool of impact melt. This pool begins as a turbulent mixture of molten and partially molten material from both the asteroid and the upper crust. Above and around it, layers of breccia form composed of broken fragments of older rocks, welded together by melt or compacted under pressure. Farther out in the outer part of the excited zone, rocks are fractured and faulted but not fully melted, recording high strain in shatter cones and other deformation structures. All of this happens while the transient cavity is still forming. At its maximum extent, this cavity in the Chicxulub event may reach depths of tens of kilometers and diameters exceeding 100 kilometers, far larger than the final visible depression. Its floor lies well below the pre-impact surface, and its walls are steep, perhaps too steep to remain stable, under the pull of gravity once the vigorous excavation phase subsides. The upper parts of the cavity walls overhang or stand at angles near the limit of stability for the materials that compose them. The excavation stage gives way almost seamlessly to the modification stage as gravity begins to dominate the evolution of the crater. The deep, steep-sided cavity cannot persist in its initial form because the rocks in its walls and floor, though shattered and heated, still have weight and finite strength. Under gravity, the walls slump inward, sending large blocks of crust sliding and rotating toward the center along listric faults that curve downward and outward. These collapsing blocks form terraces or step structures on the inner walls of the crater, each terrace representing a massive segment of crust that has detached and moved inward and downward. At the same time, the floor of the transient crater responds to the sudden unloading caused by excavation. The removal of overlying rock reduces the confining pressure on deeper materials, and these materials attempt to rebound upward. This central uplift, driven by the elastic and plastic response of the crust, causes a column of deeper rock to rise toward the surface in the center of the crater. For an impact as large as Chicxulub, the uplift can overshoot the level of isostatic balance so that the central region rises higher than its eventual equilibrium height, before collapsing outward again. The interplay between inward slumping of the walls and upward rebound of the floor produces a complex pattern of motion. In very large impact structures on Earth and other planetary bodies such as the Moon, this pattern often leads to the development of a peak ring rather than a single central peak. In a peak ring crater, the central uplift collapses and spreads outward, forming an annular ring of uplifted blocks at some distance from the geometric center, while the very center remains relatively lower. The Chicxulub structure belongs to this class. As the central uplift rises and then collapses, it drags rocks from kilometers' depth toward the surface. These rocks, initially part of the middle crust, are transported upward along complex fault networks, passing through zones of high strain and partial melting. When the motion slows and stops, they come to rest as part of the peak ring, now standing closer to the surface than they were before the impact. Surrounding them, slumped material from the walls and overlying melt and breccia fill in the central depression and bury earlier features. The modification stage continues beyond the immediate mechanical collapse. Hot impact melt remains mobile for some time, flowing under gravity into low areas, ponding in the central basin and infiltrating fractures and voids. Over minutes to hours, this melt begins to cool and crystallize from the outside, inward, forming thick sheets of igneous rock that may be several kilometers thick directly above the deepest, most heavily shocked zone. Clasts of older rock become embedded in this melt as it freezes, preserving a record of the pre-impact crust within the new igneous body. Above the melt sheet fall back breccias and swivites, which are mixtures of melted and unmelted fragments, settle as the turbulent atmosphere and plume above the crater lose energy and allow material to rain back down. These deposits help fill the transient cavity and contribute to the eventual smoothing of its floor. At the surface, the rim of the crater stands as an uplifted ring of deformed rock, raised above the surrounding terrain. This rim reflects both the displacement of material during excavation and the outward collapse of the walls. It may stand several hundred meters to more than a kilometer above the pre-impact surface, and is accompanied by an elevated ring of fractured and faulted crust beneath. Interior to the rim terraces mark the boundaries of large slumped blocks. Exterior to it, the ejecta blanket covers older sediments and rocks, with layers of breccia melt fragments and reworked material. The thickness of this blanket decreases with distance from the crater, and its coarse, chaotic character gradually gives way to finer layers at greater remove. In the minutes and hours following the impact, seawater responds to the new topography. The shallow sea that once covered the carbonate platform has been temporarily displaced by the fireball and the influx of energy, but gravity pulls water back toward the basin. As the water returns, it interacts with the still hot rocks, generating steam and additional local disturbances, and it begins to deposit new sediments atop the impact-formed units. The precise sequence of water withdrawal and return depends on details of basin geometry and the timing of larger-scale waves that propagate outward, but at the scale of the crater, the basin transitions from a dry incandescent cavity back toward a partially flooded depression. Over longer timescales, this depression will act as a local sink for sediments delivered from nearby land and shelf areas, progressively burying the impact structures under younger layers. Deep within the crust beneath the crater, heat from the impact melt and from the shocked rocks above diffuses outward. Thermal gradients remain steep for many thousands of years. Hydrothermal systems develop as seawater, and pore fluids circulate through the fractured crust, heated by the hot rocks at depth and rising through cracks and faults. These fluids can alter minerals in surrounding rocks, deposit new minerals in veins, and modify the physical properties of the crust. Such systems are common in large impact structures, and in the case of Chicxulub would have persisted long after the initial excavation, and collapse phases ended, leaving additional signatures in the mineralogy and chemistry of the crater rocks. When the rapid mechanical phases complete, the Chicxulub crater has taken on its characteristic multi-ring form. The final structure includes an inner zone of impact, melt, and breccias resting on heavily shocked basement rock. A peak ring composed of uplifted and collapsed middle crustal material, a series of terraced walls formed by slumped blocks, and an uplifted outer rim underlain by a ring of faults and fractures. The apparent diameter of the main crater is on the order of 150 to 200 kilometers, while the zone of structural disturbance in the crust extends even farther. The depth of excavation is considerable, but infilling by melt and breccia reduces the depth of the final cavity compared with the deepest point of the transient crater. Above this final crater, the atmosphere and ocean continue to adjust to the new configuration, while beyond the immediate region the energy released at impact has begun to propagate outward as seismic waves and disturbances in the air and water. Within the footprint of the crater, however, the most intense phases of shock excavation and collapse have already passed within a remarkably short time, leaving behind a large, hot and structurally complex basin that will cool subside and slowly fill with sediments over millions of years. Around the margins of the basin that will one day be recognized as the Gulf of Mexico, the impact manifests first as an intense blast of air and a pulse of ground motion that radiate outward from the new crater. Within a radius of a few hundred kilometers from the impact site, the blast wave in the atmosphere arrives within minutes traveling at several times the local speed of sound. The sudden jump in pressure crushes and shatters exposed materials, snapping tree trunks, stripping foliage, and flattening forests and coastal vegetation in a broad ring. Immediately behind the pressure front, air rushes outward at extreme speeds, generating winds strong enough to uproot large plants, roll or displace large animals, and scour soil and loose sediment from exposed surfaces. Structures of rock that already stand in a fractured state along faults or bedding planes may topple or crumble under this combination of overpressure and lateral wind. The blast does not move as a simple wall, but as a complex turbulent front, with reflections and refractions from hills, cliffs, and coastlines that create local zones of enhanced or reduced damage. Yet the overall effect near the crater is widespread mechanical devastation of the surface environment. Almost simultaneously, the ground beneath these regions experiences intense shaking as seismic waves generated by the impact travel outward through the crust and mantle. Near the crater, the accelerations far exceed those of typical tectonic earthquakes. Bedrock flexes and vibrates, sedimentary layers shear and slip, and slopes fail as landslides. Submarine slopes at the edges of continental shelves or carbonate platforms may collapse, sending slurries of sediment downslope along the seafloor. Liquefaction of water-saturated sediments can occur, allowing grains that were previously locked together to move more freely, further destabilizing slopes and foundations. The seismic energy radiates outward in multiple wave types, including compressional and shear waves that travel through the solid earth, and surface waves that roll along the crust, affecting regions far from the crater over the following minutes and hours. Within and just beyond the crater, however, the shaking is dominated by the immediate response to excavation and collapse, described earlier, producing a complex and prolonged sequence of ground motions. The presence of a shallow sea over the impact site ensures that water is displaced on a vast scale. In the first instance after impact, much of the water column directly above the crater is vaporized or blown aside by the fireball, and the shock leaving a transient cavity in the ocean surface as well as in the crust below. Gravity quickly acts to refill this void. Water rushes back toward the center from all sides, colliding in the middle and overshooting, rising into a central peak of water that then collapses again. This oscillation, combined with the continuing movement of the seafloor during crater modification launches, waves that propagate outward as tsunamis. Near the impact site, wave heights reach hundreds of meters, towering over any existing coastal relief. As these waves move away from the source region, their heights decrease, but their wavelengths remain very long, allowing them to carry energy across entire ocean basins with little loss. Around the Proto-Gulf of Mexico, these tsunamis reach nearby coasts in a short time, inundating low-lying areas, eroding shorelines and transporting large blocks sediment and organic material inland. In some locations, water surges up river valleys, reversing the direction of flow and depositing marine sediments far above previous high water marks. Where coastal plains border the sea, floodwaters may move tens of kilometers inland before retreating, leaving behind chaotic layers of sand, gravel, and ripped-up vegetation. Farther out on the continental shelf, strong currents and repeated wave passage resuspend sediments, creating turbid flows that deposit new beds of sand and silt in deeper water. The pattern of inundation depends on local bathymetry and topography, but across the region these waves act as one of the most visible immediate agents of change in the coastal and marine landscape. In the air above and around the crater, the expanding fireball continues to radiate intense heat. Within the near-field, surfaces exposed to direct line-of-sight heating can reach ignition temperatures for dry plant material. Forests and other vegetation, that have survived the initial blast or stand slightly beyond its most destructive zone may catch fire as leaves and branches absorb radiant energy. In areas where the blast has already stripped foliage and left litter and woody debris on the ground, this material can serve as fuel that ignites under the thermal pulse. Flames spread outward, assisted by the strong gusty winds that accompany and follow the shock front, producing wildfires over wide areas near the impact. These fires are not yet global in extent, but regionally. They add another layer of disturbance, converting living biomass into char and ash, and further altering the surface cover. Coarse ejecta returning to the region contributes additional mechanical and thermal effects. Blocks of rock launched on ballistic paths begin to fall back within minutes, raining down on areas surrounding the crater. Large fragments may travel hundreds of kilometers before landing, impacting with enough energy to excavate secondary craters and to generate localized shockwaves and fires. Closer to the crater, the ejecta blanket builds up rapidly, as thick deposits of mixed rock fragments melt clasts and glassy droplets accumulate on the surface. These layers bury pre-existing soils, plant communities and surface features under meters to tens of meters of new material. In shallow marine environments around the crater, ejecta falls into the water column, where it may remain suspended for a time before settling to the seafloor, mingling with tsunami deposits and resuspended shelf sediments to create complex stratified sequences. The atmosphere over the region becomes filled with dust, ash, and vapor. Clouds of fine particles rising from the fireball and from burning vegetation mix with water vapor from the ocean and from vaporized target rocks. Local visibility drops as particulate loads increase, and sunlight reaching the surface near the crater is reduced even before any broader global effects develop. As hot gases rise from the impact site, they entrain air from below, setting up strong convection that helps carry material to higher altitudes. In the lower atmosphere, turbulent flows mix warm and cool air masses, generating additional local storms and gust fronts, as the system begins to adjust toward a new equilibrium. Over the first hours, the immediate region transitions from one dominated by direct blast and thermal effects to one in which secondary processes become more important. Fires burn along broad fronts, generating their own convection and smoke plumes. Tsunami waves reflect and refract from irregular coastlines and basin boundaries, interacting to produce complex patterns of run-up and drawdown. Seismic aftershocks occur as faults and fractures created or reactivated by the impact adjust to the new stress field in the crust. Submarine slides triggered during the main shaking continue to move downslope, sending slurries of sediment across the seafloor and contributing to turbidity currents that flow along channels and into deeper basins. In continental interiors adjacent to the Proto-Gulf and neighbouring seas, disturbances propagate outward. Forest closer to the impact site may be flattened, defoliated, or burned, while those at greater distances experience more moderate damage such as broken branches, toppled trees, or limited fire spread. Animal communities face immediate mortality from blast heat and flooding. Large terrestrial vertebrates in the zone of highest overpressure are killed outright by mechanical forces. Others drown in tsunami-driven floods, are buried under ejecta or landslides, or perish in wildfires. Aquatic organisms in nearshore environments are subjected to rapid changes in pressure, temperature, and water chemistry as hot, debris-laden floodwaters move through their habitats. Some individual organisms survive in sheltered refuges, burrows deep water, or areas shielded by topography, but the overall density and structure of ecosystems close to the impact are altered drastically in a short time. At the scale of the crust, the broader region around the crater now contains a ring of heavily deformed rocks that record the passage of seismic energy and the mechanical collapse of the crater. faults and fractures penetrate outward from the main structure, providing pathways for later fluid flow. In some areas, blocks of crust are uplifted or tilted, changing local relief and drainage patterns. The combination of uplift at the crater rim and subsidence in the central basin modifies regional gradients that control how rivers flow and where sediments accumulate in the following thousands to millions of years. In the immediate aftermath, however, these long-term geomorphic consequences are only beginning. The dominant signal remains the abrupt high-energy disturbance delivered by the impact into the atmosphere, ocean, and crust of the Proto-Gulf region, expressed in blast-shaking waves, fires, and rapid deposition of ejecta and tsunami-borne sediments. As hours pass, the most violent motions decay. Winds from the initial blast subside tsunami waves, after making several crossings and reflections within the basin, gradually lose energy, and seismic shaking diminishes as the crust relaxes. Fires continue to burn in patches and lines that reflect the distribution of fuel and the earlier pattern of blast and heating, while smoke and aerosols rise into the atmosphere. At the surface, a devastated zone now encircles the crater, marked by stripped and burned vegetation, altered coastlines, thick blankets of new sediment, and a central basin of hot, newly formed impact rocks, in which the water is only beginning to return. Outside this ring, disturbances still occur, but are weaker, grading toward regions where the immediate mechanical and thermal effects of the impact are minimal or absent. Even though distant consequences carried by ejecta and atmospheric changes will later reach far beyond the boundaries of the Proto-Gulf. Beyond the devastated ring around the Proto-Gulf of Mexico, the energy of the impact continues to move outward, in the form of ejecta fine particles and vapor that spread around the planet. In the first minutes to hours, this material leaves the immediate vicinity of the crater in a broad, expanding shell. Larger fragments of rock launched at high speeds, but still below escape velocity, follow ballistic paths that carry them hundreds to thousands of kilometers away before they fall back to the surface. Smaller fragments, molten droplets, and vapor rise much higher in some cases, reaching the upper atmosphere and even moving briefly above the densest layers of air before gravity draws them back. The coarse component of ejecta consists of blocks and clasts of rock that remain solid or only partly molten during their flight. Near the crater, these pieces land quickly, contributing to a thick, chaotic blanket of mixed material that buries pre-existing landscapes. At greater distances, blocks still arrive, but they are fewer and separated by larger gaps, forming isolated secondary craters where they strike. Each large fragment carries enough kinetic energy to excavate a local pit shatter surrounding rock or sediment and generate its own small shockwave and plume of debris. These secondary impacts add a finer scale of disturbance to regions that are already experiencing shaking, flooding, and blast effects from the main event. Beyond the range of large blocks, the character of the ejecta changes. Molten droplets formed when rock from the target and the asteroid is melted and flung into the air, cool as they travel through space and through the upper atmosphere. Surface tension pulls them into roughly spherical shapes before they freeze, producing small glassy beads known as spherules, and related forms sometimes called microtectites. Their sizes span a wide range from fractions of a millimeter to several millimeters across, and their compositions reflect mixtures of crustal and projectile material that have been homogenized at high temperature. As they cool, crystals may grow within the glass or along its edges, recording in their textures the rapid quenching and subsequent thermal history of the droplets. These spherules and fine fragments are numerous. Countless trillions of them are launched on trajectories that carry them around the planet. Some remain in ballistic arcs that never leave the atmosphere. Others rise above the densest layers of air and then re-enter at high altitude and high speed. When they begin to fall back, they interact strongly with the air, their small sizes giving them very large surface area compared with mass. As they plow into the atmosphere at hypersonic speeds, friction and compression heat their surfaces. Individually, each spherule is too small to retain heat for long, and many of them radiate away their energy quickly and decelerate without melting completely. Collectively, however, the flux of re-entering material over large areas of the planet can be enormous. The energy that these particles deposit into the air is spread through a layer at high altitudes where they slow down and cool. In this layer, the re-entering spherules and associated dust add large amounts of heat to the atmosphere, which then radiates part of this energy downward as infrared and visible light. The result under some conditions is a strong thermal pulse at the surface. Modelling studies suggest that in many regions this radiative heating may be sufficient to raise the temperature of exposed surfaces by several hundred degrees Celsius over a short period, enough to ignite dry vegetation. In such a scenario, even areas far from the immediate blast zone around the Gulf of Mexico may experience widespread ignition of plant material as the global shower of spherules reaches its peak and atmospheric layers radiate energy downward. At the same time, some environments remain more resistant. Moist forests, wetlands, and regions recently inundated by tsunami or rain may not burn as readily. Surfaces that lack significant fuel, such as bare rock desert dunes, open water, and deep ocean basins absorb and re-radiate the heat without supporting flames. The distribution of wildfires therefore depends not only on the intensity of the radiative pulse, but also on the availability and dryness of combustible material, and on local weather conditions at the time of re-entry. Geological indicators from later studies point to extensive but not absolutely uniform burning, suggesting that many landscapes are affected while others escape complete combustion. Along with molten droplets and coarse fragments, a great mass of finer dust and vapor also leaves the impact site. This component arises when rock and water are vaporized during the initial shock, then cool and condense into small particles as the expanding plume mixes with surrounding air and loses energy. The finest particles, with sizes comparable to those of volcanic ash and smaller aerosols, can remain suspended in the atmosphere for long periods. Driven by convection within the rising plume, these particles reach the stratosphere, and in some cases even higher altitudes where the air is thin and vertical, mixing with lower layers is limited. Once there, high-altitude winds begin to spread them around the planet in bands that follow prevailing circulation patterns. The chemical composition of this fine material includes components from carbonate and evaporate rocks, in addition to silicate material. Carbonate breakdown releases carbon dioxide and other gases, while sulfur-bearing evapораtes generate sulfur dioxide and related compounds. In the upper atmosphere, sulfur dioxide can react with water vapor to form tiny droplets of sulfuric acid, creating a veil of reflective aerosols. These droplets scatter and absorb sunlight, altering the way radiation passes through the atmosphere. Fine silicate dust and ash also scatter light and serve as nuclei for cloud formation. Trace metals derived from the impactor, such as iridium and other elements that are rare in Earth's crust, but more abundant in primitive asteroids, are mixed into the dust and spherules. As the particles settle out of the atmosphere over time, these elements become concentrated in a thin layer that coats surfaces in both marine and continental settings. The thickness of the layer varies, but globally, it often amounts to only a few centimeters or less of material, an apparently modest deposit given the scale of the event that produces it. In the oceans, falling spherules, dust and aerosols settle through the water column, mixing with suspended organic matter and planktonic remains. Some particles dissolve or alter chemically on the way down, while others arrive on the seafloor relatively intact. the pattern of deposition depends on water depth currents and biological activity, but in many basins a thin bed of ejecta, rich clay spherules, and chemically distinct minerals forms on top of pre-impact sediments. In continental environments, the same fallout settles on soils, lake bottoms, river floodplains, and surfaces of rocks and plants. In places where fires burn ash from combusted vegetation, mixes with silica-rich spherules and mineral grains, creating dark carbon-rich layers. In wetter regions or those receiving heavy rainfall soon after the event, the ejecta layer is reworked by runoff slumping and small-scale erosion so that the original stratification becomes blurred or graded into underlying and overlying sediments. Despite this reworking, a distinct interval of unusual material still forms across many landscapes. The timing of this global fallout is rapid compared with typical sedimentary processes. A large fraction of the spherules and coarse dust returns to Earth's surface within hours, to days of the impact, while finer particles and aerosols remain aloft much longer. During this initial period, the planet experiences a shower of extraterrestrial and impact-derived material that is largely independent of local weather and geography, so that both oceans and continents receive a coating of ejecta. In shallow seas, fallout mixes with tsunami deposits and with disturbed shelf sediments mobilized by waves and seismic shaking. In deeper basins, it settles more quietly through the water column, creating relatively undisturbed layers. Over low-relief continental interiors, it may accumulate on surfaces that have been flattened or stripped by blast and fires, forming thin, laterally extensive sheets of fine material. As this global dispersal proceeds, the composition of the atmosphere changes. Water vapor, carbon dioxide, and sulfur gases from the impact mix with background atmospheric components. The presence of abundant aerosols at high altitude affects how sunlight and outgoing infrared radiation interact with the atmosphere. The optical depth of the stratosphere increases, meaning that more sunlight is scattered back to space or absorbed before reaching the lower atmosphere and surface. At the same time, smoke from fires, dust lofted by winds over disturbed landscapes, and additional ash and gases from any impact-triggered volcanic or geothermal activity contribute further to the particulate and gas load, especially in the lower atmosphere. For now, the immediate significance of these changes lies in the physical presence of a thickened, more reflective atmospheric veil and in the rapid deposition of a distinctive ejecta blanket across the globe. The long-term climatic and ecological consequences of reduced sunlight, altered chemistry, and widespread fires develop over days, months, and years after the impact. At this stage, shortly after the event, Earth carries a newly formed crater in the Proto-Gulf region, a broad zone of regional devastation around it, and a thin emerging global shell of impact-derived dust spherules and aerosols that encircle the planet and begin to filter the light that reaches the surface. In the weeks and months after the Chicxulub impact, the atmosphere and surface of Earth adjust to the injection of dust aerosols and gases released during the event, and the most important changes for climate arise from the way this material alters the flow of sunlight and heat. Immediately after impact, a large fraction of the ejecta falls back to the surface in the form of spherules, coarse dust, and larger fragments, and much of the incandescent debris that heats the lower atmosphere during re-entry cools relatively quickly. At the same time, however, finer particles and sulfur-rich gases remain aloft at high altitude, forming a persistent veil that wraps around the planet. This veil blocks and scatters incoming sunlight, reducing the amount of energy that reaches the lower atmosphere and surface. The result is an interval sometimes described as an impact winter, a period in which reduced sunlight leads to darkened skies and cooler temperatures over much of the globe. The primary agents of this radiative change are small particles and droplets in the stratosphere, and to a lesser degree the mesosphere. Sulfur dioxide released from vaporized evaporate rocks in the target region and from other sulfur-bearing materials moves upward with the rising plume and mixes with water vapor at high altitude. There, under the influence of sunlight and atmospheric chemistry, it converts into tiny droplets of sulfuric acid. These droplets, only a fraction of a micrometer across, are highly effective at scattering visible light back to space and at absorbing some wavelengths of radiation. Fine silicate dust ash and other aerosols accompany them, adding to the scattering and absorbing capacity of the stratospheric layer. Because vertical mixing between the stratosphere and the lower troposphere is relatively slow, these particles can remain suspended for years before they settle or are removed by chemical reactions and downward transport. As the stratospheric aerosol layer builds, the character of daylight at the surface begins to change. Direct sunlight weakens and more of the remaining light arrives as diffuse illumination scattered from all directions rather than as a strong beam from the sun. Under clear sky conditions, the sky may take on a hazy or milky appearance, with colors altered by the changed scattering properties. In regions with additional smoke from fires, the lower atmosphere also holds large amounts of soot and organic particles that further reduce visibility and filter light. Clouds form and evolve within this altered radiative environment, influenced by the availability of aerosol particles that serve as cloud condensation nuclei and by changes in temperature gradients between the surface and higher layers. The net effect of this combination is a reduction in the total solar energy reaching Earth's surface. With less incoming shortwave radiation, the lower atmosphere and ground lose heat to space more quickly than they gain it, and average surface temperatures begin to fall. Climatic models that incorporate realistic estimates of aerosol loading and radiative transfer suggest that in the months following an impact of Chicxulub scale temperature drops at the surface can be large, especially over continents and in the interior of large land masses. In some scenarios, mean annual temperatures in mid-latitude continental regions fall by several tens of degrees Celsius, relative to pre-impact values for a period of years, while ocean surfaces which have greater thermal inertia cool more slowly and by somewhat smaller amounts. The magnitude and duration of cooling depend on the total mass particle size distribution and vertical placement of aerosols, which in turn depend on details of the impact and atmospheric circulation that are still subject to uncertainty. Superimposed on this global cooling, regional variations arise from the distribution of land and sea, the pattern of winds, and the presence or absence of additional smoke from fires. Continental interiors, far from the moderating influence of oceans, may experience more extreme swings between cold nights and weekly warmed days under the dimmed sun. Coastal and oceanic regions respond more slowly as the upper layers of the sea release stored heat and buffer the air temperature. High latitudes, which depend on low-angle sunlight even in normal conditions, can see more pronounced reductions in illumination during their winter seasons, extending periods of deep cold. The tropics, although still warmer on average than higher latitudes, lose much of their earlier thermal advantage as the reduction in solar input is proportionally large compared with other regions. Alongside the cooling of the surface, the vertical temperature structure of the atmosphere changes. With more aerosols and soot absorbing sunlight in the stratosphere and upper troposphere, those layers can warm relative to pre-impact conditions, even as the surface cools. This altered temperature gradient affects the strength and position of jet streams and large-scale circulation cells, modifying patterns of winds and storms. The exact changes depend on the evolving aerosol load and on feedbacks involving clouds and water vapor, but in general the circulation shifts away from its late Cretaceous baseline toward a state with weakened surface heating and altered meridional temperature contrasts. Precipitation patterns respond to these changes. Reduced evaporation from cooler ocean surfaces leads to overall declines in atmospheric moisture, and regions that previously received abundant rainfall may enter extended dry periods. Monsoon systems, which rely on strong seasonal contrasts in land and sea temperatures, weaken or fail as those contrasts diminish. In some models, a drier, colder climate spreads across continental interiors, while some coastal and equatorial regions retain more frequent rainfall. At the same time, where localized temperature gradients remain strong, storm tracks can become more variable, producing episodes of intense precipitation separated by longer dry intervals. Another consequence of the altered atmospheric chemistry is acid precipitation. Sulfur dioxide and nitrogen oxides in the atmosphere react with water vapor and oxidants to form sulfuric and nitric acids. When these acids dissolve in cloud droplets and fall as rain or snow, they lower the pH of surface waters and soils. In the months and years immediately after the impact, episodes of acid rain may be common, especially downwind of regions where sulfate aerosols are concentrated. Freshwater lakes, small streams, and shallow soils are particularly sensitive to such inputs as they have limited buffering capacity. In these environments, acidification can dissolve carbonate minerals, mobilize metals and stress, or kill organisms that are adapted to narrower chemical ranges. In the oceans, acid input from the atmosphere arrives mainly at the surface through dissolution of carbon dioxide and acidic aerosols. The breakdown of vaporized carbonate rocks at the impact site releases large amounts of carbon dioxide, adding to pre-existing greenhouse gas levels. On longer timescales, this additional carbon dioxide can contribute to warming, but in the immediate aftermath of the impact, the cooling effect of stratospheric aerosols dominates. While the aerosol veil persists, the enhanced greenhouse forcing from carbon dioxide remains largely masked by the reduction in incoming solar energy. Over years to decades, as the aerosols settle and wash out, and as the stratosphere returns toward its pre-impact clarity, the residual increase in greenhouse gases can begin to influence climate more strongly, potentially driving a rebound toward warmer conditions. The balance between short-term cooling from aerosols and longer-term warming from carbon dioxide is one of the central questions in reconstructions of post-impact climate. Geological and modelling studies indicate that severe cooling and reduced sunlight lasting at least several years are robust features, whereas the exact magnitude and sign of longer-term temperature changes over tens to hundreds of thousands of years remain less tightly constrained, influenced by carbon cycle feedbacks, ocean circulation adjustments, and interactions with other processes such as volcanism. For ecosystems, the most immediate global effect of darkened skies and cooling is a sharp reduction in primary productivity, photosynthesis. The process by which plants, algae, and cyanobacteria use sunlight to convert carbon dioxide and water into organic matter depends directly on the flux of light at specific wavelengths. Under an impact winter scenario, the combination of dimmed sunlight, lower temperatures, and in some regions ice and snow cover drastically reduces the rate at which primary producers can fix carbon. On land, many plants lose leaves to fires, blast, or cold. Some forests and plant communities experience dieback as light levels and temperatures drop below their tolerance thresholds. Evergreen species adapted to lower light may survive in part, especially where temperatures remain within their physiological range, but many other plants enter dormancy, fail to reproduce, or die. Seed spores and underground storage organs provide some capacity for later regrowth, once conditions improve, but during the period of darkest skies, net primary productivity on land decreases sharply. In the oceans, surface-dwelling phytoplankton are similarly affected. The aerosols and dust in the atmosphere reduce the intensity of light reaching the sea surface, and particles in the water column themselves can scatter and absorb light, further diminishing the amount that penetrates to depths where most photosynthetic organisms live. Cooler surface waters may become more strongly stratified in some regions or in others. Enhanced cooling may increase, mixing that brings nutrients to the surface. In either case, if light falls below critical levels, even nutrient-rich waters cannot support high rates of photosynthesis. Some plankton groups may endure better than others, depending on their pigment composition, depth preferences, and ability to form resting stages that sink to safer depths. Overall, however, the marine primary productivity that sustains food webs built on plankton declines markedly during the period of weakest sunlight. The combined impact of cooling darkness, altered precipitation, and acid deposition unfolds over varying timescales. The initial severe reduction in light and temperature may last a few years to a decade as stratospheric aerosols slowly clear. During this time, many organisms that depend indirectly on continuous primary production, such as large herbivores and planktivores, face shortages of food. Some survive by exploiting stored energy refuges with less severe conditions or flexible diets. Others succumb as the base of the food web temporarily fails to support pre-impact population levels. In subsequent decades, as sunlight returns more fully, and temperatures begin to rise from their minimum values, the climate moves out of the impact winter phase, but the ecological and geochemical systems do not simply return to their prior state. Surviving plant and algal communities expand into newly available niches, while soil chemistry, ocean alkalinity, and the carbon cycle adjust to the pulses of acid input and carbon dioxide. Volcanic activity, including large-scale eruptions that may already have been ongoing before the impact, continues to inject gases and aerosols into the atmosphere, potentially interacting with the post-impact recovery trajectory. Among scientists, the relative contributions of the impact-generated aerosols soot from global fires and volcanism to the detailed shape of the climatic downturn and rebound remain active subjects of study. Despite these uncertainties, the core picture is clear. Following the Chicxulub impact, Earth experiences a period in which skies are substantially darkened. Global surface temperatures drop, precipitation patterns shift, and acid deposition affects land and water chemistry, and this period imposes severe stresses on primary producers and, through them, on the food webs that depend on continuous flows of energy from sunlight into ecosystems. As the period of darkened skies and cooling settles over Earth after the Chicxulub impact, the consequences for life on land unfold through the progressive weakening and collapse of food webs that have taken tens of millions of years to develop. The immediate mechanical effects of blast fires and flooding around the impact site cause extensive mortality in that region, within hours to days, but the global extinction patterns that mark the end of the Cretaceous arise mainly from slower cascading failures driven by loss of primary productivity, altered climate and chemical stress over years to decades. On the continents, plants form the base of most food webs, converting sunlight, carbon dioxide, and water into organic matter that supports herbivores, omnivores, and indirectly predators and scavengers. When the stratosphere fills with aerosols and dust and sunlight at the surface weakens, this conversion slows sharply. Many plants that survive the initial fires, blast, and acid rain lose their leaves, fail to flower, or suspend growth under low light and cold conditions. Some evergreen species persist longer, but even they must contend with reduced photosynthesis, and in many regions with drought as cooler oceans evaporate less water and precipitation declines. In the worst affected areas, whole forests die back as trees exhaust their energy reserves, and cannot replace damaged tissues or maintain essential physiological processes. Grasses are not yet a dominant component of late Cretaceous landscapes, but ground cover plants, shrubs and understory flora also suffer as their light environment and water supply change. Seeds, spores and underground organs such as rhizomes and bulbs represent latent stages that can survive adverse periods, and these propagules remain in soils and sediments even when adult plants die. Spore-producing plants adapted to disturbed ground may find opportunities once light and moisture return, but during the impact winter, the living biomass that actively fixes carbon declines to a fraction of its former level. The animals that depend directly on this vegetation feel the effects quickly. Large herbivorous dinosaurs, which in many regions dominate the role of primary vertebrate consumers on land, require substantial amounts of food to maintain their bodies and activity. Herds of hadrosaurs, ceratopsians, and other plant-eating dinosaurs that previously moved through forests and floodplains feeding on leaves, twigs, and reproductive structures now encounter landscapes with reduced foliage, scorched stands, and increasingly bare branches. In areas where fires are extensive, the available plant material is converted to char and ash, and becomes temporarily unusable as fresh food. Cooler temperatures may allow some short-term preservation of remaining biomass, but reduced plant growth means that the supply is no longer replenished. Even if individual animals survive the initial post-impact years by drawing on stored fat, or by reducing activity, many populations cannot support reproduction and juvenile growth without reliable food. Young dinosaurs which grow rapidly and require high energy intake are particularly vulnerable to shortages. Similar pressures act on other large herbivores such as some mammals and reptiles, but because the largest mammals at this time are much smaller than the largest dinosaurs, their absolute food requirements are lower and their feeding strategies more flexible. As herbivores decline, predators feel the consequences with some delay. Large theropods, including tyrannosaurids in parts of what will become North America and Asia, depend on abundant prey to sustain their own populations. In the immediate aftermath of the impact, carcasses of animals killed by fires, blast, and acid rain provide a temporary surge of food for scavengers and carnivores. This pulse supports scavenging communities and may allow some large predators to survive for a short time even as live prey becomes rarer. However, once this one-time resource has been consumed or decayed, the absence of thriving herbivore populations leaves predators with little to hunt. Large-bodied carnivores with high energy demands and low reproductive rates are especially prone to decline under such conditions. Their populations fragment, individuals range more widely in search of food, and many eventually disappear as the base of the vertebrate food web weakens and fails. Smaller omnivores and insectivores on land, including many mammals, lizards, and some birds, experience the same broad environmental stresses but have different capacities to survive them. Many small mammals can shelter in burrows, crevices, or dense ground cover, protecting themselves from the worst of fires, blast winds, and temperature extremes near the surface. Their diets often include seeds, insects, and detritus resources that may persist longer during a drop in primary productivity than leafy vegetation does. Insects, fungi, and bacteria continue to break down dead organic matter, even under low-light conditions, although their rates of activity depend on temperature and moisture. Detritus-based food chains therefore remain functional in some soils, and leaf litter supplying food for small animals that can exploit them. Seeds and spores stored in the ground or in seed banks carry condensed energy that some small vertebrates can use, especially if they have adaptations for caching or for feeding on hard, nutritionally dense plant structures. In these microhabitats, life remains active even as large vertebrate faunas collapse. Motor patterns and life histories also influence survival. Animals that can lower their metabolic rate during periods of stress, enter torpor or hibernate, have advantages in surviving extended intervals of food scarcity and cold. Some mammals, reptiles and amphibians possess such abilities to varying degrees. Burrowing habits not only provide physical shelter from fires and blast, but also help buffer temperature and moisture extremes, as soil temperatures change more slowly than air temperatures. Aquatic and semi-aquatic animals that can retreat into ponds, lakes and rivers may also find refuges where temperature fluctuations are moderated and where detrital food chains remain active. These traits do not guarantee survival, but they shift probabilities. In contrast, many large non-avian dinosaurs are tied to surface environments, lack deep burrowing behavior, and appear to rely on high sustained metabolic outputs related to active lifestyles. Their eggs are laid in nests at or near the surface where environmental conditions strongly influence incubation success. Prolonged cold, heavy acid rainfall and unstable weather patterns disrupt nesting and reduce the viability of eggs, adding another layer of stress beyond adult survival. Among dinosaurs, the contrast between non-avian forms and the lineages that give rise to modern birds provides a striking example of differential survival. Birds at the end of the Cretaceous already span diverse habitats and diets, with some adapted to aquatic environments, others to forest canopies, and others to ground-dwelling niches. Fossil and molecular evidence suggests that most large-toothed birds and many specialized forms disappear at or near the boundary, while a subset of small-bodied, mainly toothless lineages persists. Various hypotheses link this survival to combinations of small body-sized flexible diets that include seeds and other durable foods, and the ability to shelter in relatively protected environments such as dense vegetation or near water. In this view, birds that can exploit seeds, insects and detritus during periods of low primary productivity may have fared better than larger herbivorous or predatory dinosaurs that depend on continuous plant growth or abundant large prey. However, the detailed reasons for the survival of particular bird clades while others vanish remain under study, and the fossil record is incomplete, so reconstructions rely on patterns rather than individual histories. Other reptile groups on land show varied responses. Crocodilians, which in many late Cretaceous regions inhabit rivers, lakes and coastal wetlands, survive the extinction in several lineages. Their semi-aquatic lifestyle, slow metabolisms and capacity to go long periods without food under cool conditions may contribute to this resilience. Turtles, many of which are also linked to aquatic or semi-aquatic environments, and have protective shells, likewise persist in multiple lineages, although some forms disappear. Squamates, including lizards and snakes, show a mixed pattern, with some lineages dying out and others continuing into the Paleogene. Amphibians, which rely on moist habitats and often have life cycles tied to water, also appear to fare relatively better than many large terrestrial vertebrates, though they too experience losses. Mammals as a group pass through the extinction with substantial survival at the family level, even though some specific lineages may terminate. Their small sizes, diverse diets, nocturnal or crepuscular habits, and use of burrows or other shelters likely play roles alongside reproductive strategies that include internal gestation and the ability to care for young after birth. On land plant communities, as they respond to the impact winter and its aftermath, show stages of collapse and reorganization that feed back into animal survival. In many areas, fires and cold reduce dense forests to stands of charred trunks and open ground. Spore-producing plants that thrive in disturbed soils can colonize quickly once light returns to usable levels, and their rapid life cycles allow them to cover large areas in a relatively short time. flowering plants and conifers, which often have more complex reproductive cycles, and slower growth, may take longer to re-establish their previous dominance. The timing and sequence of plant recovery differ among regions depending on local climate, soils, and the severity of initial disturbance. During the early recovery phases, landscapes in some places become dominated by low, fast-growing vegetation that supports different animal communities than the tall, diverse forests of the late Cretaceous. This turnover in plant types reshapes the resources available for herbivores and influences which animal lineages can expand or reoccupy particular niches. The timescales over which these terrestrial changes occur vary. The most acute stresses related to darkness, cold and acid precipitation likely peak within a few years after the impact, a period in which many large specialized terrestrial animals disappear. The fossil record, which typically resolves events on timescales of thousands to tens of thousands of years, captures this interval as a sharp turnover in many sections, with the last occurrences of numerous non-avian dinosaur species and other large reptiles tightly clustered near the impact ejecta layer. On longer timescales of tens of thousands to hundreds of thousands of years, plant communities reorganize, soils redevelop, and surviving animal lineages diversify into new forms. From the perspective of the extinction event, however, the key feature is that the combination of impact winter conditions, fires, habitat destruction, and disrupted reproduction produces a global collapse of many land-based food webs in a geologically short interval. The end result on continents is a biosphere in which non-avian dinosaurs and several other prominent reptile lineages vanish as major players, while small mammals, birds, crocodilians, turtles, amphibians, lizards, and a subset of plant groups persist in refuges and disturbed landscapes and begin as conditions slowly stabilize to occupy ecological spaces left open by the extinction. The precise pathways by which each clade navigates this transition differ and remain the subject of ongoing research, but the broad outcome is a marked reduction in terrestrial diversity at large body sizes and a restructuring of land ecosystems around smaller, more generalist and often more shelter-capable survivors during and immediately after the impact-induced climatic downturn. In the oceans, the aftermath of the Chicxulub impact brings a different but equally severe set of stresses transmitted through light temperature chemistry and the structure of food webs that begin with microscopic producers in the sunlit surface layer. Before the impact, late Cretaceous seas support diverse communities of plankton invertebrates, fishes, and large marine reptiles. Ammonites, with their coiled shells and complex sutures, occupy many ecological roles as active swimmers and drifters. Planktonic foraminifera, single-celled protists that build calcium carbonate shells, float in the upper water column and form a major part of the microfossil record. Calcareous nanoplankton, including coccolithophorids that produce tiny plate-like structures of calcium carbonate, contribute heavily to marine primary production in many regions, their remains accumulating as fine limestones on the seafloor. Large reptiles such as mosasaurs and plesiosaurs hunt in open waters and long continental margins, sharing these seas with sharks, rays, teleost fishes, and a great variety of invertebrates on shelves and slopes. When the impact injects dust aerosols and gases into the atmosphere, one of the earliest global oceanic consequences is the reduction of light reaching the sea surface. During the period of impact winter, the intensity of sunlight that penetrates the upper layers of the ocean falls well below late Cretaceous norms. In the photic zone, where photosynthetic organisms depend on light energy to fix carbon, this drop in illumination leads to a strong decline in primary productivity. Phytoplankton cells in the upper tens of meters of water experience conditions that in many regions no longer support normal growth and reproduction, Some groups respond by forming resting stages or sinking to deeper, more stable layers, but others cannot maintain their populations under the combined pressures of reduced light cooling and potential changes in nutrient supply. The decline in primary production cascades quickly to higher trophic levels in the marine food web. Zooplankton that feed on phytoplankton, including many small crustaceans and protozoans, lose their main food source. Some can graze on detritus and bacteria or feed opportunistically on the remains of organisms killed by the initial disturbance, but overall energy flow through the planktonic food web diminishes. Small fishes and invertebrates that depend on these zooplankton encounter lower prey densities and must expend more energy searching for food. Over time, population sizes of these consumers shrink as mortality exceeds reproduction. Larger organisms such as ammonites and many pelagic fishes feel the effects as their prey base contracts. Simultaneously, the chemistry of surface waters begins to change. Acid rain delivers sulfuric and nitric acids to continental surfaces, lakes and rivers, and runoff carries dissolved ions and altered sediments into coastal seas. In the open ocean, dissolution of carbon dioxide and other gases from the atmosphere modifies the carbonate system, affecting pH and the saturation state of calcium carbonate minerals. The breakdown of carbonate rocks at the impact site itself releases carbon dioxide, which eventually contributes to this process. In the near term, while aerosols still block much sunlight, the cooling and reduced gas exchange at the surface complicate the immediate response of ocean chemistry, but on timescales of years to decades, surface waters in some regions likely become more acidic than before the impact. Organisms that secrete calcium carbonate shells or skeletons are particularly sensitive to changes in carbonate saturation and pH. Planktonic foraminifera and calcareous nanoplankton, which build their shells from dissolved ions in the near-surface waters, face conditions that make shell formation more energetically costly or unstable. The combination of reduced food availability, altered chemistry, and temperature stress leads to high extinction rates in many of these groups at or near the time of the impact. In contrast, organisms that build siliceous skeletons, such as some radiolarians and diatoms, may be less directly affected by carbonate undersaturation, although they still experience the consequences of reduced light and cooling. Benthic foraminifera, which live on or in the seafloor sediments at greater depths, show a different pattern from their planktonic relatives. Many benthic species survive the extinction interval, though some turnovers occur. One reason may be that deep-sea environments already dark and relatively cold before the impact are buffered against short-term changes in surface conditions. Organic matter continues to rain down from the surface layer, and while its flux may decrease during the impact, winter detritus-based food chains in deep seabed communities still function to some degree. Moreover, the chemistry at depth responds more slowly to changes in surface pH due to mixing timescales and the existing structure of ocean circulation. In this way, deep benthic communities may experience stress but not the same abrupt collapse seen among many surface dwellers. Among larger marine animals, the extinction pattern is uneven but severe. Ammonites disappear entirely along with belemnites and several other cephalopod groups that formerly play major roles in midwater and nectonic ecosystems. The reasons for their complete extinction likely involve a combination of reduced food for their larval and juvenile stages' sensitivity to changes in water chemistry and reproductive strategies that include planktonic phases vulnerable to disruptions in the surface environment. Many marine reptiles, including mosasaurs and plesiosaurs, vanish as well. These large predators depend on robust populations of fishes, cephalopods, and smaller reptiles to sustain their high-energy lifestyles. When prey densities fall, competition among predators increases, and any reduction in reproductive success can rapidly drive populations downward. Their life histories, which probably involve long generation times and slow reproduction compared with smaller fishes and invertebrates, further reduce their ability to recover from a sudden environmental shock. Sharks and rays, by contrast, pass through the extinction with significant survival at the family and higher taxonomic levels, although some species and lineages vanish. Their cartilaginous skeletons, diverse feeding strategies, and wide geographic distributions may provide resilience. Many sharks are opportunistic feeders capable of switching between prey types, and some can exploit carcasses and detritus as well as active prey. Their reproductive strategies vary, but some produce relatively few well-developed offspring, which may have a better chance of survival in harsh conditions if suitable refuges exist. Teleost fishes, already diversified by the late Cretaceous, also fare comparatively well in aggregate, although again with losses in some lineages. Their flexibility in habitat use, diets, and reproductive modes allows at least part of the group to find niches in altered environments. In nearshore and shelf regions, the physical disturbance caused by tsunamis, seafloor slides, and sediment resuspension reshapes habitats. Coral communities, sponges, and other sessile organisms are buried in some areas under blankets of debris, while in others, scouring removes sediment and exposes hard substrates. These changes, combined with altered water quality and chemistry, lead to high mortality in many reef-building organisms. Reef ecosystems that rely on tight coupling between symbiotic algae and animal hosts are particularly sensitive to temperature and light changes, and under prolonged low light and cool conditions these symbioses break down. The result is a reduction or disappearance of many reef frameworks during and immediately after the impact interval, with consequences for the vast number of species that depend on reef structures for habitat feeding and protection. Open ocean ecosystems also contract. Regions that once support high plankton productivity and diverse pelagic food webs see a decline in biomass at all levels. Migratory patterns where they exist are disrupted as temperature gradients and current structures change. Some taxa retreat toward refuges where conditions remain more tolerable, such as upwelling zones where nutrient-rich waters still support some primary production, or polar and subpolar regions where pre-impact temperatures are lower, and organisms may be better adapted to cold and variable light. Others shift depth distributions, moving into mid-water layers that offer greater stability, though at the cost of reduced access to surface-derived food. The degree of oxygen depletion in the oceans during this period is a topic of active research. In some scenarios, reduced mixing and ongoing respiration in the deep ocean could lead to expansion of low oxygen zones, stressing organisms that require well-oxygenated waters. In others, cooler surface waters and altered circulation patterns might increase ventilation in particular basins. The geological record shows evidence for changes in redox conditions in some marine sediments across the boundary, but these signals are not uniform, indicating that oxygen levels vary regionally rather than following a single global pattern. As the years pass and the aerosol veil begins to thin, sunlight gradually returns to the surface of the ocean, and temperatures start to recover from their minimum values. This recovery is not instantaneous, and the biological systems that respond have been reshaped by the preceding crisis. New primary producers or surviving ones in altered proportions begin to recolonize the photic zone. In many regions, small opportunistic species that reproduce rapidly take advantage of the newfound availability of light and nutrients released from decaying biomass and eroded terrestrial inputs. Plankton communities reorganize, with some groups that suffered heavy extinctions remaining rare or absent while others expand. Calcareous plankton assemblages in the earliest post-impact intervals are often dominated by small, simply structured species that can tolerate variable conditions and may cope better with residual acidification and nutrient pulses. Over tens of thousands to hundreds of thousands of years, more complex communities slowly re-emerge, but they differ in composition from those of the late Cretaceous. Bivalves, gastropods, and other benthic invertebrates recolonize shelf and slope environments as sediments stabilize and water quality improves. In places where reefs once stood, new reef-like structures form only gradually. Some coral lineages survive and eventually rebuild frameworks, while in other regions different organisms such as larger bivalves or sponges occupy structural roles. Fish faunas diversify into the altered seascapes with teleosts, sharks and rays, exploring ecological opportunities left by the disappearance of ammonites, many reptiles and some older fish lineages. In deep sea settings, the rain of organic matter from the surface regains strength as primary productivity recovers. Benthic foraminifera and other sediment-dwelling organisms adjust to the new food regime, and those lineages that survive the extinction proliferate into new species. The carbonate compensation depth, the depth at which calcium carbonate dissolves as quickly as it accumulates, may shift in response to the pulse of carbon and acid entering the ocean, affecting where calcareous sediments can accumulate without dissolving. Over time, as the carbon cycle and ocean alkalinity adjust, carbonate deposition stabilizes and new layers of limestone and chalk begin to build again atop the boundary interval. From the perspective of marine ecosystems, the key outcome of the impact and its climatic aftermath is a sharp, geologically rapid extinction of many groups strongly tied to surface productivity, carbonate shell building, and specialized reef environments, coupled with a better survival rate among organisms that rely on detritus, occupy deep or buffered habitats, or possess broad tolerances and flexible diets. The oceans do not become sterile, but their community structure changes. Large marine reptiles and ammonites, which once symbolized late Mesozoic seas, vanish, while sharks, teleost fishes, some cephalopods, and many benthic invertebrates persist, and over longer timescales radiate into new ecological niches. The early stages of this recovery begin as soon as light and temperatures rise enough to permit renewed primary production, but full re-establishment of complex, diverse marine ecosystems requires hundreds of thousands to millions of years, during which the legacy of the impact and the end Cretaceous extinction remains visible in the composition and distribution of marine life. Long after the impact itself, when the crater has cooled, subsided, and become buried under younger sediments, the event remains recorded in rocks around the world as a set of subtle but diagnostic signals. In many places, these signals lie within a thin band of sediment that marks the transition between the last rocks of the Cretaceous and the first of the Paleogene. This boundary is now recognized as the interface associated with the end Cretaceous mass extinction, and the Chicxulub impact stands at its center as the dominant physical disturbance that coincides with the disappearance of many species on land and in the oceans. In marine and some continental sequences, the boundary often appears as a thin clay-rich layer sandwiched between more massive units of limestone, sandstone, or other sedimentary rocks. Below it, late Cretaceous strata contain abundant fossils of organisms such as non-avian dinosaurs on land, diverse ammonites and large marine reptiles in the seas, and rich assemblages of planktonic foraminifera and calcareous nanoplankton. Above it, early Paleogene rocks show a markedly different fossil content, with many late Cretaceous forms missing, and new assemblages of surviving and emerging species taking their place. Within the boundary lay tiny glassy spherules, shocked minerals, and anomalous concentrations of certain elements record the passage of impact-derived material through the environment and its incorporation into the sedimentary record. One of the most striking chemical signatures in this layer is an enrichment of iridium and other elements that are rare in Earth's crust, but relatively abundant in primitive asteroids. Iridium normally occurs at very low levels near the surface because during Earth's early differentiation, it partitioned strongly into metallic phases and sank toward the core. When measurements of boundary layer sediments reveal concentrations of iridium far above typical crustal values, this suggests an addition of material from an extraterrestrial source. The pattern of enrichment, often sharp and confined to a narrow interval, is consistent with the rapid deposition of a global blanket of ejecta, rather than with slow, steady input from background sources. Alongside iridium, other siderophile elements such as nickel and cobalt appear in ratios similar to those found in certain classes of meteorites, reinforcing the interpretation that the boundary layer incorporates debris from a single large impactor of carbon-rich chondritic composition. Microscopic examination of grains within the boundary clay reveals further evidence of extreme shock. Quartz and other common minerals show planar deformation features sets of closely spaced parallel lamellae within individual crystals that form only under very high pressures associated with large impacts or nuclear explosions. Glassy spherules and microtectites, sometimes altered to clay minerals over time, preserve shapes and internal textures that reflect their origin, as molten droplets ejected from a hot expanding plume and cooled while flying through the atmosphere. Their compositions, when analysed, match mixtures of crustal rocks and impactor material expected from the Chicxulub target region, including contributions from carbonate and evaporate strata. Some spherules display internal crystallization patterns or vesicles that record degassing and rapid quenching, linking them to the high-energy conditions near the impact plume. These spherules and shocked minerals occur not just near the Gulf of Mexico, but at many widely separated sites on different continents and in deep sea cores, indicating that material from the impact spreads around the globe and settles through both air and ocean water into a worldwide layer. The thickness and detailed makeup of the boundary deposit vary with distance from the crater and with local depositional environments. In areas relatively close to Chicxulub, the layer may include thicker beds of coarse ejecta, reworked tsunami deposits, and mixed volcanic lastic and impact-derived material. In more distant deep sea settings, it may consist of only a few millimeters of clay, rich sediment containing scattered spherules and a strong iridium anomaly. In some continental basins, the original boundary layer has been eroded, reworked, or buried beneath younger deposits, but patches remain that preserve the key signals. Where multiple sections from different parts of the world are compared, a consistent picture emerges of a globally synchronous narrow time interval marked by the fallout from a major impact. Correlations between boundary layers in different regions rely not only on geochemical markers, but also on biostratigraphy and magnetostratigraphy. Below the boundary, late Cretaceous assemblages of planktonic foraminifera, calcareous nanofossils and other microfossils occur. Above it, these are replaced by distinct early Paleogene assemblages. This sudden shift in fossil content appears in many marine sediment cores and outcrops, suggesting a rapid turnover in plankton communities. Similarly, the last appearances of numerous ammonite species and of many groups of marine reptiles coincide closely with the boundary. On land, the final records of non-avian dinosaurs in many regions occur just below the boundary clay with no evidence of their continued presence in overlying younger sediments. Magnetostratigraphy, the study of past reversals in Earth's magnetic field recorded in rocks, provides an independent temporal framework. Sedimentary and volcanic rocks acquire a remnant magnetization that preserves the direction of the magnetic field at the time of their formation. By matching patterns of normal and reversed polarity intervals in boundary, bearing sequences to a global polarity timescale, scientists can determine the age of the boundary and place it within a precise chronological context. Combined with radiometric dating of minerals in volcanic ash layers and of impact-related materials such as melt rocks and spherules, these methods converge on an age of about 66 million years for the boundary and for the Chicxulub impact itself. High-precision isotopic dating of zircon and other minerals in the impact melt sheet and ejector layers indicates that the time difference between the impact and the deposition of the boundary layer is very small in geological terms, consistent with a single catastrophic event rather than a series of widely separated disturbances. The Chicxulub crater itself, largely buried beneath younger sedimentary rocks of the Yucatán Peninsula and the floor of the modern Gulf of Mexico, was not recognized at the surface in the way that some large impact structures on other planets are. Instead, its discovery and confirmation as an impact site come through geophysical and drilling studies. Gravity surveys detect a circular anomaly where rocks beneath the surface are less dense than surrounding areas, reflecting the presence of thick impact melt and breccias. Seismic reflection and refraction profiles reveal a complex multi-ring structure with a central uplifted zone, a surrounding peak ring terraced walls, and an outer ring of faults matching the form expected for a large impact basin in the upper crust. Boreholes drilled into this structure encounter characteristic impact lithologies, thick sheets of melt rock overlying heavily fractured basement impact breccias and suavites, with mixed melted and unmelted clasts. Within these units, shocked minerals and high-pressure phases confirm that the structure results from an impact rather than from volcanic or purely tectonic processes. The diameter of the main crater inferred from these geophysical and drilling data on the order of 150 to 200 kilometers matches that expected from an impact by an asteroid of roughly 10 to 15 kilometers in diameter. Chemical analyses of melt rocks and breccias show mixtures of crustal materials consistent with the known stratigraphy of the Yucatán carbonate platform and underlying basement, along with traces of chondritic composition that point to the presence of extraterrestrial projectile material. The depth and morphology of the crater align with modeling of impacts into layered targets that include shallow water and carbonate sequences, further linking this particular structure to the type of impact described in earlier sections. The integration of crater evidence with the global boundary record and extinction patterns forms the basis for treating the Chicxulub impact as the primary driver of the end Cretaceous mass extinction. The temporal coincidence between the impact age and the boundary, the worldwide distribution of impact-derived ejecta, at that level the sudden loss of many taxa at or immediately above the boundary in multiple environments, and the physical plausibility of the climatic and ecological effects of a large impact winter all support this interpretation. At the same time, geological records show that other processes, particularly large-scale volcanism, such as that recorded in extensive basaltic lava flows emplaced in what is now India, occur in the same broad interval around the Cretaceous-Paleogene transition. These eruptions release gases and aerosols that can influence climate and ocean chemistry over longer timescales, and their interaction with the impact-generated disturbances remains an active area of research. Some studies suggest that volcanic activity contributes to long-term environmental stress before and after the impact, potentially affecting recovery and the exact shape of extinction curves, while the impact provides the abrupt global shock that delivers the final rapid collapse of many ecosystems. Others explore how the impact might modulate or even accelerate volcanic outgassing by disturbing mantle and crustal conditions. The relative contributions of these factors are not yet fully resolved, but the presence of a large, well-dated impact crater and a global ejecta layer at the extinction horizon provides a clear anchor point in the complex sequence of events. In cores and outcrops today, the boundary appears as a quiet thin line of altered clay, densely packed microfossil remains, and unusual chemical signatures that belies the scale of the disturbance it represents. Above it, Paleogene sediments accumulate, gradually recording the slow recovery and diversification of surviving lineages in a world without non-avian dinosaurs and with restructured marine and terrestrial ecosystems. Below it, late Cretaceous rocks preserve the record of a biosphere dominated by those now vanished groups. Between them, in only a few centimeters of material at many sites, lies the record of the Chicxulub impact, and its immediate aftermath encoded in iridium-enriched clays, shocked minerals, glassy spherules, and abrupt changes in fossil assemblages that together allow reconstruction of the event's timing, magnitude, and consequences from the perspective of deep geological time.